All right, everybody, welcome back. Hope lunch was good over in the other room there. So a couple of quick points I wanted to make before we got started again. First of all, I love all the questions that have been coming in. I'm really glad you guys are engaging with the material like this. It's great. So please keep this coming in, both asking me and putting those on the doc for as many questions as there are there. There are answers coming in from the TAs as well. So that's really great. Keep that up. Excuse me. Second thing here is I set up this tentative schedule. I updated that a little bit based on what we were able to get through this morning. So the morning got shifted around a little bit. We're going to knock out the clickstream 04 notebook for the first half hour here, and finish that up by actually thinking about a different view of that clickstream data, a sort of more graph-based view, quickly speeding through that graph frame kind of demo notebook there. From there, we'll spend about the next hour talking about a machine learning pipeline, looking through a little bit of the NLP stuff. And then how Spark ML allows you to set up a pipeline, train your model, save it off, load it back, and make predictions with it. And then from there, we'll be at about 3, so we'll start to talk about Spark streaming, take a break, and then spend the rest of the afternoon talking about Spark streaming, the old version, and then the new API that's coming out, Spark structured streaming, which is going to be really cool. So that's pretty much the plan. And without further ado, let's get back into, I was just poking through this. The 04 DA clickstream notebook here. Hopefully this is a reasonable size, looks good. Cool. So we're changing data sets here to look at Wikipedia's clickstream data. So what's going on here is basically we get a sort of table where, here I can just show you and it's a little bit easier. We get a table of a bunch of click-throughs, all right? So we see that this person clicked onto a particular page. So for some of these, it's exclamation point, exclamation point. These appear to be sorted. But we're going to see that under cur title, so that the page the person has clicked onto. We're going to see where they came from in prev title, so that's the refer. So in some cases, we see here that's going to be Google or other Wikipedia or empty. Empty is typically HTTPS traffic, or a title of another page that this person clicked through as they were going through Wikipedia. So that's kind of the data we're going to be looking at. And then we're going to ask a few questions here. How much traffic is coming from Google? These kinds of questions. What's refer traffic looking like? What are some of the articles that people click through to the most on Wikipedia? Just taking the top 10 there. Who was Wikipedia's biggest external referrer? And kind of other questions along those lines. We can take a look at some missing pages that we might want to make new, or missing articles that we might want to make new Wikipedia pages for. And some of the inflow and outflow considerations in this more tabular manner. And then, as you can see, questions like inflow and outflow are already starting to lend themselves to a more graph-based analysis. As for the internal stuff we're going to look at, this is kind of the final notebook today where we're really talking about some internal considerations with Spark, some of these lower-level data frame APIs specifically, as well as how we can best tune our jobs, make sure to correctly partition our data in particular, so that we're best utilizing our cache and this sort of thing. So any questions on that introduction? Cool. Yeah, so this is just a diagram here of that click stream as someone clicks through, so you could imagine tracing those along. And we will do that in the graph frames notebook, which should be cool. So this time we saw above that we were looking at a TSV file, right? And as discussed this morning, when we're looking at like a TSV or a CSV file, we cannot easily infer the schema without scanning through that file at least once. So in order to avoid that extra scan, we're going to again set up our schema just as we did in the previous notebook by importing our SQL types, setting up a struct type, and importing all our fields. Again, this is just based on what we've already kind of examined. We've already done a head on the data, examined it, so we can see what's going on there. Cool. So I know a substantial portion of this room has only used Spark 2, so this is something you don't need to worry about too much. But basically, for anyone who's ever dealt with CSVs before, CSV parsing can always be a headache, and there are always subtle things we have to worry about. I believe we have to worry a little bit about quote parsing here, and how Spark 1.6 versus 2.0 correctly parse quotes. In any event, beware of that. If you are someone who's coming from 1.6 to 2.0, you might have some concerns around CSV loading. And in particular here, what we do for this data is there is a quote option we can set that allows us to correctly parse this data set because of the way quotes are escaped in the CSV file. Always a lot of fun parsing different people's versions of correct CSV. Cool. So because we have, again, explicitly set that schema, this is now a lazy load. We don't need to scan the data at all. And so it just takes half a second here to instantiate this data frame object. So then when we click display, we're actually going to have to load in some data to take a look at this in our nice tabular format. So we can see here again, we have both the previous ID, current ID, as well as the previous title and current title. So these are just parallel fields where this one's human readable and this one is Wikipedia readable. N is going to be the number of clicks that followed the same path from Google to the exclamation point page. So we can just start to take a look here. How many records do we have? Again, we could, if we were using something like Parquet here, we would just have this for free. We don't have this metadata for free, so we do our explicit count. So this is going to take a moment here. Cool. I'm going to keep moving through that. And this is all just explaining what I was just talking about in terms of what these different columns are. So the first thing we're going to do is get rid of some of the fields we don't need. For this particular analysis, we don't need those previous and current IDs. So we're just going to take a look at the previous title, the current title, number of clicks. Oh, and the type field there. Cool. So this is now getting back into the point of talking about how we want to correctly partition all of this data, or this particular data set, and the concerns. So I really want to kind of highlight this here. So what I'm going to do is open up again the Spark UI, so we can start thinking about this clickstream data. We already saw above, and I kind of skimmed through this, that we actually have a decent amount of data in this data set, right? We're looking at 1.3 gigabytes, I want to say, of data. So this is a point where things start to get a little bit less trivial in terms of the size of the data we're analyzing, right? The earlier stuff, a couple hundred megabytes, in terms of what our cluster can do. So let's take a look at, in the Spark UI, the storage tab. Oh, and I have some stuff cached. If you do not want to see this cache, you can restart your cluster. And actually, maybe, yeah, I'm going to skip on doing that. There should not be anything here. There is for me. That's fine. So we see that I already have some stuff cached, and we can already see that I guess here we're using a bunch of data in memory already, right? We have a bunch of different chunks here. We have a few 64 megabyte chunks, as well as this 80 megabyte chunk. Yes, this is from the GraphX notebook I was just looking through. But we already have a bunch of stuff cached, including a gigabyte of data cached here. So that kind of makes sense if we're doing an exploratory analysis, right? We're going to have some stuff cached. We've been looking around. Now, when we click over to the executors tab, as I just did, we can take a look at exactly how much memory we have in each executor JVM devoted to storage, right? So we already talked about the fact that this executor has 3.6, 3.7 gigabytes of memory. Some of that is going to be devoted to actual operations and processing that we need to do, right? But as you can see here, we have actually 2.1 gigabytes of memory devoted to storage. So I think this raises 2 points. Number one, you can already see that I here am getting close to this limit. You guys are probably going to be less close there. But we do have this limit. Number two, of 3.6 gigabytes, 2.1 gigabytes is a pretty substantial amount, right? So intelligently using this caching is going to be something that's really, really important, and is sort of up to you to make sure you're caching the right things so that your jobs will run quickly, right? And that is sort of by design. That is something that is for you to do. There are configuration parameters, I believe, that let you set the amount of memory you want to have allocated for in-memory storage versus other operations and whatever sort of swap space you need in memory. But for now, we have that set to 2.1 gigabytes by default. So by default here, we have 10 partitions, right? So that's based on the S3 chunking that's going to be coming in. So as we're running through here, there's a pretty good chance that we're going to overflow our cache space, right? So given that, we want to take two things into consideration here while we cache. Number one is the first point we've been talking about, which is the number of cores we have in our executor, right? So we already looked at that with the spark.conf master. We saw that we are running a local cluster with 8 executors, or excuse me, 8 cores in our executor, right? So that's point one. Point number two is we now have the potential for cache eviction. So maybe we don't want the entire partition that's currently allocated to a core to be thrown out of the partition and sent back to disk to have to be reloaded, right? So instead of just doing a naive 8 here, what we're going to do is set it to 16. So that means we have 2 smaller chunks of data. So if one of those gets evicted, then in all likelihood, the other partition is going to remain in memory. We're a little bit safer for that sort of cache eviction scenario. So let's run through this, set that configuration. So then from there, the first thing we're going to do is take our data frame, repartition it into 16 partitions, create a table so that we're actually going to see some SQL querying below. We're going to set up that cache and materialize it. So this will take a moment. Any questions on that so far? Sure.
So in the code command create table, are we creating a table out of the cache?
In the create or replace temp view line, is that what you're asking, or?
Cache table.
Oh, sure. So again, the question here is around what's happening with the create or replace temp view, and then we load up a Spark table and call .cache on that. Again, this is an equivalent way of caching the initial data frame. In this case, we are just registering a temporary table that we're going to be able to use for those SQL-like queries and then caching that, but that is, again, identical to just saying .cache on this data frame. which is why we can then say .count on the data frame itself to materialize the cache on the table. They're just different views into the same data. So okay, so
Question.
sure.
Essentially that memory, 2.1 gig, so whatever is the cap on the file size that we can analyze at this point, or?
So the question is 2.1 gigabytes the cap on the file size that we can analyze? The answer there is no. You could conceivably analyze much larger data sets here. What the 2.1 gigabyte number is going to be is the amount of data that we can actually store in memory cached, right? So Spark performs best when our data is in memory. This is one of the kind of big advancements, right, over Hadoop, is that we don't write to disk, pull back, write to disk for each step of our job. We keep that in memory as much as possible. So you can have a scenario where you're analyzing larger data sets, you write your intermediate results back to disk, pull it back. But this is the 2.1 gigabytes is the amount where Spark is going to remain especially performant, right? Because we can load that all into memory. Cool. So now that we've kind of cached that, we can take a look at what's going on back in the Spark UI. So you can see here I have a bunch loaded, and it actually looks like, for me, a bunch of that information oh yeah, we're good. A bunch of the other information has managed to remain in memory because of the fact that while our data set was 1.3 gigabytes uncompressed, when we take as sort of like raw string TSV data, when we actually load this into memory in the nice Spark, again, we're talking, remember the tungsten format, it's only 922 megabytes. So we get a little bit of compression there, and we can see here our chunk sizes are slightly less than 64 megabytes, which is kind of nice. They're down to 57. And these are all, again, just on the same executor because we only have one executor. Cool. So yeah, so again, continuing along with this sort of caching discussion, the ideal range, so a way to think about how many partitions should I be using aside from the just number of executors and cores that you have that are going to go out to those tasks. Aside from that, a good just rule of thumb here is about 50 to 200 megabytes for any given partition. That's about how much space you want each of those to be taking up in memory. And that's, again, some combination of where Spark's going to be most performant, the number of executors we have, and then making sure that only small chunks of data are evicted from the cache that we can easily reload from disk. Cool. So that being said, we only have 8 cores, right? So that means that we're going to have 2 partitions effectively on each core, which means when we actually run our job, each core is going to have to take care of 2 tasks because we have 1 task run per partition, right? So we had a first stage that was skipped here, but you can see that we have, again, 16 tasks run, 1 for each partition. And if we look into the Spark UI at this particular job, look at our tasks on this stage. I'm going to close this out. Okay, so we can't see exactly which thread each of these was run in because we only have 1 executor. But you can see that all 16 tasks were run on the same executor. And basically each core there is going to have to take on 2 tasks. Cool. So this is just going to alias the data frame so that now we actually look at some analysis. And now that we've gotten things kind of nicely partitioned, we can run through this and just give us a nicer name to work with. Cool. So the first question we want to ask here is, how much traffic was referred to the Apache Spark page by Google in the time frame of our data set. So we can do that pretty easily here with two filters. First of all, we want to say that the current title is Apache Spark, and the previous title was coming from Google, or excuse me, the previous page was Google, right? And once we do that, we see that aggregate number is right there for us. We have about 14,000 of those. So that's a pretty simple one. So here's a question: how many unique articles did Google send traffic to? So I'll give everyone a minute here to think about writing that query, and I'll give you a hint. We're probably going to want to use a distinct here, right? Or do we even need to? See a few people typing away. But yeah, so you don't actually need to use a distinct here because, again, each row has the aggregate number already present for us. So if we want to know the number of unique articles, each row corresponds to one refer article pair. We just need to filter down to all of those refer article pairs where the referrer is Google. So we take account of that. And we see that there are about 2.5 million. And take a note of how quickly this is running. You know, we were because of the correct partitioning and caching that we did here on this 1.3 gigabyte data set, which is I think 3 or 4 times bigger than what we were looking at before. We're still able to run this filter and count in 2 seconds. So the next question here, top 10 articles requested from Wikipedia. So what we're going to do is just group by the current title. So that, again, is the page that people are currently on. So we're going to get requests from all referrers, right? And then we're taking the sum there and just showing 10 of those. So if we want the top 10 articles, we're going to have to do a little bit more, right? And in particular, we're going to have to do an order by. So if you're following along, feel free to take a stab at this while I type my version in. What I would start by doing is just kind of copying and pasting this initial query here. And then we're going to do an order by. So this is a bit tricky here, right? How are we going to reference this column name? Does anyone know?
As.
Oh, sure. Someone in the crowd suggested as, which is a thing we could do if we were a little bit fancier up here. We could actually alias this column using the as command to say, instead of calling this sum of n, let's be a little bit smarter. I'm going to actually be less smart and actually just reference it as the name that we get from the .sum function call, which is a perfectly fine way of doing it. And then we're going to need that in descending order. I'm going to limit that to 10, and we'll do it the same way that we saw above with a display call in the Databricks interface. So I think one interesting point to note here is that although we just did this group by, the point that we have cached from is clickstream df2, right? So this is the point, this is the object that we have stored in memory. So now every time we call this group by, we have to do the whole group by again. So that's going to be kind of the most time-consuming operation here is the group by and the resultant shuffles that we need to do. But once we run that and we take our sum, sort it on the sum n column name, we see here that in fact the main page is the most requested page on Wikipedia. Everyone goes to the main page, or a lot of people at least do, which is maybe a little bit surprising. Usually, I kind of click through Google to go to a particular page. I guess in February of 2015, it was the Oscars, so people seem to be really looking up, 50 Shades of Grey, which was nominated for an Oscar. And all the movies then, I think Birdman won that year. Cool. So now that we've done a little bit of that, the kind of I think the last thing I really want to demo in this notebook, or I guess there are two more points I want to make in this notebook. The first one here is Spark SQL. So as mentioned before, the reason we keep doing this create or replace temp view call is so that we can then run SQL commands like the one that you see here. So rather than doing the clickstream df2 dot select, and I think we could actually put a star in there, or clickstream df2 dot limit 6, we're going to write this as a SQL query where we're selecting all the columns from this table that we've sort of registered up here. We're going to select all those columns and limit the results back to 6. And then once we do that, we can feed it into the nice Databricks display function. Note that if we don't do that, we still get a data frame back, right? So you can kind of see here that regardless of the syntax that we're using, we're working with the same underlying engine, and that translation back and forth between tables and data frames is pretty seamless. And now I could do a group by here or something like this if I wanted to. So going through here, this is just taking the query we did above and writing it in SQL. So for the SQL, the people who really like SQL here, and I know that was a pretty big proportion on our pre-class survey, this is a really nice way of analyzing data in kind of a more natural, expressive way that you're used to. So we can always do, no matter what Spark environment we're in, we can always do spark.sql and then enter in our query string. In Databricks, we can actually use this %SQL magic command and get this nice syntax highlighted SQL that's going to do the exact same thing, and then this is going to return back for us. I forget, is this going to give us back a display or a data frame? Yep, it gives us back also the display in the Databricks view. But you can again see this is the same group by we were doing before, just in SQL. Sure, question?
Query perform the same way?
Sorry?
Will the performance?
Yeah, so the question is, will the query perform the same way? Yes, so it will perform exactly the same. It will be, if we were to look at the two plans, so remember the .explain step we looked at, we could actually go back into the UI over to the SQL tab and take a look at the ultimate plan, even the final physical plan that comes out of that is going to look the same. But more than that, we can then step back up and see how these two different queries get parsed into the same logical plan and then optimized from there. So yes, they're just really two different ways of running the exact same code. And they're both going to be equally as optimized and equally as good. Sure, question in the back?
With the Spark SQL, you can only access tables that you've already
You could, sorry? Yeah, you could plug into like a Hive. If you already have a Hive setup, right, you can plug into your Metastore there. And
Better than that, though. Okay, you need to be clear. I'm going to interject. Sorry.
sure.
Spark SQL is completely interoperable with data frames. Okay, but here's the problem. If you have a data frame and you store it in a variable, how do you access that? How do you access that in SQL? Right, SQL wants a table, right? So how do you reference a data frame that's stored in a variable as a table? I'm sure you've already seen Christian show you create or replace temp view. All that does is give a pretend table name to an in-memory data frame. You do that, and you can access that data frame from the SQL statement. It does not have to be a Hive table. It does not have to be a SQL table. All you're doing is giving an alias to the data frame. And the SQL statement will return another data frame. You are perfectly free to bounce back and forth between data frames in SQL with no penalty whatsoever. Okay, so use whatever makes sense to you in terms of trying to read what you've written later.
Cool. Thanks, Brian. No, thank you. Yeah, so again, really just two identical views here. Cool. And then we can see here just a nice list of the SQL functions that we have. So in SQL World, and I guess this is a good point to, or a good place to kind of stop and take a look at that. We can see here by using the explain keyword, we can again do just as we did with data frames df.explain. In this case, we're using the explain keyword at the beginning of our query in SQL, and then actually taking a look at what that plan looks like, which is kind of nice. Cool. So I think with that in mind, given the fact that we now have two ways of accessing the data, we have the clickstream table, which, as Brian mentioned, is generated right here by this create replace temp view. We have the clickstream table that we can select from in SQL, and we then also have clickstream df2, which is going to be that identical view into the same data as a data frame. Let's take a couple minutes here and try to code up in, again, whichever way is better for you. The answer to this question, which is who was Wikipedia's top referrer in February of 2015? Okay, cool. So I guess show of hands, how many people were attempting this with the SQL API? A few? And then how many people were attempting it with a data frame API? A few more? Cool. Yeah, it looks like a decent number of people were attempting though, which is great. So I did a solution here in the data frame API. Myself, I'm coming from PyData and this sort of thing, so it's the API that personally I'm more comfortable in, but it's going to be a very similar aggregation either way to what we were doing above. So you can see here that I just did a group by previous title. So again, that's going to be the referrer name. Take a sum of that, and then just sort that in descending order so we can take a look at the top few referrers there. You could also take this query basically and change this to prev title and then grouping by prev title here in SQL, and it's a query quite similar to this one for the top 10 referrers, or for the top referrers. Then we can see here that Google is the biggest referrer to Wikipedia, maybe as we'd expect. Cool. So then in Databricks, we can kind of plot that out. So let's quickly look at that functionality.
When do you use the dollar sign and when do you not? Because here, group by you're not having the dollar sign, but part of why you do need a.
Sure. So this is a good question and a good point to make. The question is right here we use the string previous title, and over here we use a dollar sign of the column name that we care about. So The difference is the data frames API will let us pass in either strings as column names or these $ column objects. So what this is actually doing is taking this string and saying, give me back a column object that will be associated to that string. Now, the reason over here we can get away with doing .prev title is because, or excuse me, prev title as a string is because we don't want to do anything else, right? Over here, we also want to sort this in descending order. So we have to use the $ to say, hey, you're not just looking at a string, you're looking at a column here, and I want that column in descending order. My recommendation here in general is to be consistent. So I know I just wrote this, but I think sort of the best practice, right, is to use the $ so that we always have column names. You can also do clickstream df2. So in some cases, like with joins, you need to be unambiguous about the particular data frame you're referencing, and $ won't be enough. So you can also reference or create these column objects in a way similar to $ that's a little bit less syntactic trickery and magic-y by using this clickstream df, or by explicitly selecting the column from the data frame with this syntax. In any event, cool, so now that we've got this shown, something kind of cool we can do is plot that out. So if you click in the display window that pops up when we call this function in Databricks, if you click on the bar chart here, or the plot, you can actually generate a nice bar chart that correctly infers the fields we want as our keys and the values we want there. But you can also specify some plot options, like what kind of plot you want, and this sort of thing. Cool. So again, as we were talking about right at the end, we can import our SQL functions again. And again, to highlight that point, we have SQL functions here inside of our data frame that we can call on the columns, right? So again, we use $ here. But again, we can also, as we saw above, once we have these functions imported, we could do in SQL spark.sql. That's the correct syntax, right? Yep. We could do spark.sql select some n from, we call this clickstream, right? Or we don't even need to do that. So we run that query, and again, we get a data frame back, right? Just highlighting that these are really interchangeable back and forth kind of deals. And if we write it in SQL, again, we can see we have that sum function. I could lowercase it too. And we're going to get back the same result either way. Cool. So I think in the interest of time, I'm going to leave these next few questions. While they're interesting, I'm going to leave those kind of as exercises here. But we can do some interesting analyses talking about or looking into sort of what links are missing and maybe what Wikipedia pages we'd actually want to create, right? So that's what this is all walking you through. I'd recommend going through it later. It's pretty interesting. Cool. And then the last thing we do here, which is kind of I think the last point that I want to make in this notebook, is just talking about how we can do joins of different data frames and some of the concerns around that. So I really just want to bring this up so that it's in your mind when you're thinking about joins, because this is one important sort of SQL-y, table-y operation that you have to be very careful with when you, or reasonably more careful with, right, when you're running your jobs. So the reason for this, right, is because when we do a join, we're going to have to do a whole bunch of shuffling to get keys onto into the same executors, right, or into the same cores on that executor. Basically, we're doing a giant repartition, right? So there are a bunch of different ways we can optimize this. One is if we're doing an equijoin, as we are here, and our data set is small, we can actually say, or the data set that's to be joined, the right data set, assuming we're doing like a left inner join, is small, we can actually broadcast that out to every single executor, right? Through something called a broadcast variable. Again, this is actually an optimization that's done for us in Spark 2. It's called a broadcast join, but we send that out and then we kind of avoid some shuffling. In the case of this join here, it's going to be a little bit slower because we're doing an equijoin, but then so you don't have to worry too much about that. Just kind of know that Spark is doing it for you. The final important point here is kind of, and for SQL people, you kind of are familiar with this already, right? If we were to do a Cartesian join by doing something like this, where we're doing an inequality condition and we have to take every single ordered pair, that's always going to blow up our data size, cause a bunch of shuffles, and be a big concern, right? So always just keep that in mind, that when you're doing kind of a not equality join, especially in a distributed system that's going to end up being a Cartesian join, be careful.
Is that correct what you said?
If I run this, yes, equals not, yes, this is actually the not equal, yeah, that is the correct syntax there, equals not equals. I think TAs, do you guys know, can I do not equals equals or equals not equals to the same effect?
Why would it be not equals equals?
I think just both ways are supported, and we can do either or. And we'll actually see that in a future notebook. I know that equals not equals is in a future notebook, but typically I use not equals equals when I'm doing my analysis, just in general, right? Because I think I kind of agree with you. It's more natural and makes more sense. Cool. Okay. Yeah, so then going through the rest of this, again, all really interesting stuff. We do this Sankey flow diagram that we'll actually take a look at in a moment to see what the clickstream graph is kind of looking like in terms of what page clicking people are clicking from, how they funnel to, kind of like if you ever used Google Analytics, how that clickstream looks. Cool. Yeah, so any questions on that material before we move on? Let me leave this open. Cool. So yeah, this kind of, I think this concludes a lot of the Spark API, especially data frames API deep dive stuff that we want to do today. And we're going to spend the rest of the afternoon, like I said, talking about a few of the different libraries that sit on top of Spark in this core data frames API, and let us do a bunch of really interesting analyses and this sort of thing. So the first one I want us to look at is going to be this 07 DS graph notebook. So I think I really want to briefly go through this one. It's definitely related to the clickstream data we were just looking at, which is why it's kind of interesting to do now. I know there wasn't a ton of interest in among you all in graph frames, but I do think there are a few. It's worth showing this off fairly quickly so we could think about how this clickstream data and these links between pages we can see as nodes and edges on a graph. In order to do this, we now have to actually do one more thing in the Databricks platform. So what we're going to need to do is import a couple of libraries. Graph frames, by default, is not sitting inside of Spark. This is because it's a bit newer. It is at this point stable, but the old RDD-based GraphX API is only for RDD. So this graph frames API is a way of sort of porting that into the data frames land, right? The data frames world. So let's import that. So I think in order to run this notebook, you need to follow along with me here. You need to import these libraries. So what we're going to do is we're going to go to the 00A, prepare your workspace notebook. And you're going to see there's a whole bunch of steps here, a bunch of set of instructions. Skip down through all of these and just head down to section 4, the install third-party library section. And you'll see here that there's a step-by-step list of what to do to actually get this graph frames API imported, as well as we're going to need 2 more libraries, one for using Kafka and Spark streaming, and then one more, which is actually in the class document. I'll highlight that in a moment, to parse some JSON in the structured streaming notebook that we'll be looking at towards the end of the day. So the way we can do that is, if you're following along here, you're going to want to come down to this step 4, again inside of section 4. Come down to this step 4 and copy this, oops. Yep, there we go. Copy these Maven coordinates. Once you have that copied, you can click on Workspace, then Create Library. We're going to select some Maven coordinates. If you can see here that if you have your own jars or Python packages, you can upload those really easily in the Databricks UI as well. But here we're using Maven coordinates. So you enter those in, and then skip this, skip all this, and just click on the Create Library button. Cool. So we can see the particular libraries that are getting installed there, namely the graph frames API and a couple of, I guess, logging dependencies. And we can see that went from attaching to attached pretty quickly. So now let's rinse and repeat for the other 2 libraries. And I'll give everyone a couple of minutes to do that here. The second library can be found by, again, going down to step 4. We already copied these graph frames Maven coordinates. Now we want to go down to step 5, where there are Maven coordinates for this Kafka library that we're going to need for Spark streaming. You can select that, copy it, and do the same thing. Oops. And again, we can see we need a bunch of dependencies there. So the very last library that we're going to need to import is on the class document. If you scroll down towards the bottom, you're going to see a section, Instructor Notes and Student Instructions. In that section, I put up a little note here, which are the Maven coordinates for the Spark structured streaming library, or for the JSON parsing library that we need for Spark structured streaming in order to go through that notebook. It's just a JSON parser. We can do the same thing.
I'm sorry, repeat that URL?
Sure, it's on the class document. So if you go to the tiny URL from the very beginning of class and scroll down. Yeah, just raise your hand if you're having a problem with that. The TAs are circulating, can help. Sorry? There are 2 in the prepare your workspace notebook, and then there's going to be 1 in the class document.
Why are you not using the new preview reference?
Which thing?
There's a newer version of reference instead of preview, I think.
Oh, I think it just happened to be in this prepare your workspace notebook from when we generated this thing. Yeah, but the newer version would also be fine to use.
I was obviously one of the 5 people who put yes, no one didn't know what new reference.
Cool. Yeah, I'm a big fan myself. It's really interesting.
Yeah. It's the only difference.
Hey, Kyle. Excuse me. Hey, Kyle. Oh, there's one other gentleman. Yeah, so you can confirm those libraries are there if you look in your workspace, and you'll see them as 3 new libraries in this column. Okay, I think we're pretty much good to go here for the most part. I know there are a couple people still finishing up. But yeah, I kind of want to quickly take a tour of graph frames here so that we can move into the machine learning stuff and then onto streaming and structured streaming. Cool. So what we're first going to do in here is just set the number of partitions to something smaller than 200 again. 60, I guess, is a reasonable number for this particular analysis. So the point of this notebook is to show you what graph frames can do. So to this end, we have this whole cool demonstration that we're going to walk through. However, we're using a pre-set up nodes and edges data set right? Where we've actually, you'll see we loaded in a second, it's already sort of parsed out for us and we get a nice graph from it easily. If you're interested in learning more about this stuff, and Brian, I saw you just walk back in, if you want to provide any more insight here, but this graph frames demo actually walks through the process of setting up a graph, which is in the graph frames API, which is kind of nice, including setting up the appropriate IDs and how to do that mapping, that sort of thing, on a toy example, but it will be useful if you want to better understand the kind of machinations there. So I just wanted to point that out quickly as some other good reference material that's inside of this course. So with all that said, let's start walking through this. So raise your hand if you are familiar kind of with the concept of a graph already. Nodes and edges. Okay, great. So pretty good coverage there. So we have vertices and edges. In this case, we are going to be looking at the clickstream data. So our vertices are going to be our pages, and then the edges between them are going to be clicks from one page to another, a non-zero number of clicks there, right? So each of our edges is going to be weighted based on the number of clicks that went from one page to another. So that's what we're kind of visualizing here. Under the hood, we have set up two data frames, one for the vertices and one for the edges, where we have the source and destination. Once we do that, we can instantiate a graph frame object and start to run graph algorithms on this thing. So you can see here that, again, we've already sort of pre-partitioned this for us from the clickstream data. So here we're going to load up the vertices data frame, and we can take a look at that. So we can see here we just have an ID and then title for each, we just have an ID title mapping here, right, for each vertex. And then a lot of all the information about the links, including the weights, is going to be stored in those edges. So as we move through, there are about 3 million pages represented here. So then we're loading up our separate and second edges data frame here. We can take a look at what that looks like with this show command. So we can see here, we're going to have to be a little tricky in some of the queries that we run. But we have the source ID and the destination ID, so we'll have to do some lookups there. We could also do it as a join if we wanted to, or we can use graph frames. But this is just pointing out kind of what that edges data frame looks like. We've got the source title and the destination title here. Again, just from that clickstream data, this is what we were just looking at with a separate, again, this separate kind of lookup table for the vertices. Cool. So then we see that there are substantially more edges. We've got about 22 million links from page to page. Cool. Once you import these libraries, I think you need to restart your cluster. Otherwise, you're going to see the same import error that I just saw.
You just detach the notebook and then attach it.
Oh, it does, detach and reattach does it as well? Cool. So either of those options. So while this is restarting, I'll kind of keep walking through here. So the way we start playing around with the graph frames API is after we import it, we instantiate one of these graph frame objects, again with these two data frames, the vertices data frame and the edges data frame. So as we saw, there were many more edges than nodes here. We have many more links between pages than pages themselves, right? So that's just what this is showing off, is that for each of our vertices, we're also probably going to have links. For example, there might be a link between Hadoop and Spark. I'm not 100% sure, but we might have a link going in the other direction, which we'll see in a diagram in a moment. But now that we're reattached, we should be reloading all this stuff. Great. Cool. So we can start to ask questions of the nodes or the vertices and edges data frames in our graph, right? So one of the first things we can do here is say, let's take a look at all of the links that go out from Spark, where that's the source title, to somewhere else. So visually up here, we see what that looks like. There's a link to Hadoop, Mate, and Mesos. And then when we show some of those links down here, sorting by ordering by which are the most popular, which had the most clicks in our time frame, we see some of those linked right here with their particular edge weights. So the point here is that we can just start to do some really simple queries the same way we'd expect on a data frame on our graph. Looking at our edges. We can also figure out how many inbound links are going into Apache Spark. So you can see, yeah, so there is a link between that comes from Apache Hadoop and goes into the Apache Spark page, which gives us a diagram that kind of looks like this. We see Google and HTTPS refers, and then Hadoop coming in, right? So this diagram is not actually correct, right? Because the Apache Hadoop page is one node. In our graph, we have two edges between it. And notably, we can see that here, where the destination ID for Apache Spark is this number right here, 4216, so on and so forth. And up here, that's the same source node, right? It's all the same nodes and edges pointing to each other. Cool. So I think this here is just then talking about another view or two into the Wikipedia data set we can think of in a more graphical way, right? So we can think about graphs of editors, as we do here, where we have relationships between editors and the pages they've edited. We're not going to look at that, but then again, this is just kind of other ways you can think about using graphical data where you have objects and connections between them. Objects here are pages and editors, and the connections, again, are the edits that they're making. So I think the idea with the different weights on these lines, for example, is that this person has made more substantive edits than this person to the Boeing 77X page. So we can kind of measure things that way in a graphical sense, right? We can also think about, rather than the clickstream graph, we can just think about all of the pages. Excuse me, all of the pages that a given Wikipedia page links to, and set up a graph that way, some kind of notion of a knowledge graph and closely related concepts. So the clickstream graph is only giving us the links that people have actually clicked on, right? So we get a graph of all of those relationships. So it's going to be somewhat more compact than the full link graph that we kind of see here to all of these various pages, some of which are going to be clicked on more than others, some of which might not be clicked at all. But that's another graph that we have here. And then this very last graph we have is going back to the editors and pages they edit thing. Basically, this is an analysis that's really interesting if you want to click on the link and go through, that's trying to identify malicious editors to Wikipedia, whether that's for brand reputation or for other reasons, and kind of graphing out the relationships there. So if you're interested in that and the kind of how graph analysis is used, take a look at that link. Sure.
you find friends of friends relationship in this kind of graph?
That's a really good question. And I don't believe we talk about it in this notebook. The question is, how do we find friends of friends or set up queries like this in the Graph Frames API? And actually what I would do there is point you to the other notebook I was just mentioning, the Graph Frames demo, where you can see the particular query syntax that Graph Frames allows for setting up queries like friends of friends and other relationships where we're looking for, or for example, we might be interested in pages that link in both directions, right? From A to B and from B to A. We can do that with Graph Frames does have a query syntax for that is outlined in this notebook. It's pretty cool.
Can I ask, so what are
Sure.
the main differences between the graph frame API and what we are doing? So here basically most of the functionality is already embedded as methods into graph frame. Is that
Yeah, so the question is what functionality do we get from Graph Frames? Basically, yeah, and so far we've done just sort of simple filtering stuff that we could probably do on tables, right? So what we're going to see here is we can start thinking about indegrees. So actually, yeah, let me just continue and I can kind of answer that question. Oops. So what we're going to do here is actually try to figure out the in-degree of the Apache Spark article. So quick refresher, in-degree is in this case, I think we're going to do the sum of the weights of all of the other edges that are pointing into the Apache Spark article, but the in-degree is just the number of edges that point to a particular node, right? So we're taking a moment here to get the particular ID for the Apache Spark article. So once we have that filtered out, so this is the first thing GraphX gives us for free, right? This in-degrees attribute. Or this in-degrees data frame, rather, that we can then filter on to say, show me the in-degree of the Apache Spark article. So I was slightly mistaken. This is not the sum of the clicks. This is just the strict in-degree, the number of other articles that people clicked from in our time span to get to the Apache Spark article. Then likewise, we get out degrees here, so we can do the same thing and figure out how, on the out degrees and figure out how many different articles people click to from the Spark page, and we see here that there are about 30 of those. We can generate subgraphs very easily just by filtering on the vertices as we do here. So what we're doing, right, is we are filtering out the main page, which is maybe a page on our graph that we're not so concerned about. We're not worried about people who click that Wikipedia link in the top left corner and go back to the main page. That sort of thing. So as you can see here, we're really just dropping out this one vertex to maybe get a more relevant subgraph. I think this is just showing that to continue constructing this subgraph, we want to get rid of all the edges. That were edges back to that main Wikipedia page, and you can see here that while we remove one node, we actually have to remove a ton of edges in order to construct this. And here's an answer to your question from a minute ago about the not equals equals versus equals not equals syntax. So not equals equals is in fact deprecated. You should use equals not equals. So that also explains why I've used a lot of the not equals equals before.
one more question?
Sure.
In graph frame, edges and vertices, are they aware of each other? Is there a chance to have the edge for non-existing vertex? Which means referential integrity. Is there supported, or you could load edge to non-existing vertex?
That's a good question that I don't know the answer to off the top of my head. You should put it into the document, and my guess would be we could have those references, but again, I put it.
It's problematic. I think you do
Yeah,
from edges.
exactly.
At the edges, and then
Yeah.
you will get the vertices from the edges, and then you'll avoid them.
Yeah, but we can get you the exact answer if you put something in the document.
That's what I'm saying. Is it very tight before loading? So you can actually load 1, 2, 3, which non-existing vertex and okay.
Yeah. Yeah, so please just put something in the document there. So in any event, right, so that is, I think that question about sort of what if we have empty edges or edges that point to a non-existent vertex, we could have that problem, which is why here, right, we're filtering out both vertices and edges so that as we scroll down, we do the filtering here on our edges data frame, and then we just construct a new graph to generate our subgraph, right, to make sure that we have both the vertex subgraph and the edge subgraph with a bit of filtering. So that's kind of useful. Yeah, and then I think the last thing that we're going to demo here is just this kind of fun shortest path algorithm. And it's actually going to take a few minutes to run, so you can run this on your own cluster and see the final answer. But one of the sort of most important graph algorithms, right, is the shortest path, like Dijkstra's algorithm. What's the shortest path from point A to point B? And in this case, we're saying, you've all kind of heard of the how many the Bacon number, right? Like an actor's Bacon number is how many degrees of people they are away from Kevin Bacon in terms of movies they've acted with. So if I've starred in a TV show with Ed Norton, who's been in a movie with Kevin Bacon, my Bacon number would be 2, right? Because I'm 2 people away. Kevin Bacon has a Bacon number of 0. So what we're trying to do here is find the Bacon number of Apache Spark with respect to Wikipedia links. How many clicks will it take to get from Apache Spark to Kevin Bacon? What's the shortest path there based on the graph that we have? So this is where we really start to see the power of graph frames. And in particular, we're getting the IDs that we need, the in-degrees. I'm just kind of looking at those, so you can see a lot of pages linked to Kevin Bacon, which is kind of funny and maybe as expected. And from here, what we can do is on our clickstream graph, where we have taken out the main page, so it's the subgraph, we can run the breadth first search algorithm. That's something that's given to us by graph frames. So we're going to say we're going to search from the ID for Apache Spark to the ID for Kevin Bacon, and we're going to run that. So this one takes a few minutes. So I think I'm just going to point this out so we can move on to machine learning. But then we also, in a very similar way, we can do PageRank to compute, which, for those of you who've seen PageRank algorithm before, which pages are maybe most interesting or most important based on the other links that are referring to them. So we have PageRank. And again, if you look into the Graph Frames API, you'll be able to see a whole bunch of the other functions that are implemented on graphs, these nice graph algorithms, like PageRank. And I suspect the PageRank algorithm is going to take a while too. Yeah, it says 13 minutes here. And then, like I said, the very last thing is, and I'll actually just quickly bring this up, is this notebook is constructing a graph, and what we can do is a query syntax along the lines of this. We use this .find, A to B, B to A, with an intermediate AB. So this will let us do some more interesting queries that are specific to a graph that we can't do on just a pair of node and edges data frames, at least with particularly easily, right? This is a much more natural and nice interface. Cool. So any final questions there on the graph frame stuff? Cool. All right. So I think the plan probably until about 3:15 here is going to be to take a look at some NLP and some NLP work that we can do on Wikipedia article text. So we're going to use that natural language text and start to set up an interesting pipeline for clustering. So basically what we're going to do is try to say, given a bunch of Wikipedia article text, can we figure out what topic this article would be associated with, topic modeling, right? So we're going to do that in a few steps. And the first thing we're going to do is take a look at some of the processing tokenizing feature extraction code in this notebook here. So head over to the 08 Wiki NLP student notebook. Cool. So along with kind of moving to a new topic here, we're moving to a new data set, which is again going to be that I guess March 5th snapshot of articles that were edited on March 5th on Wikipedia and all the full text there. So we have that stored here as Parquet files. There are about 660 megabytes of them. There's a subtle point here. So this is actually a point where we're running into a memory concern, where we do not have enough memory in our cluster to use Parquet's vectorized reader. So we have to disable that. Unfortunately, which means things are going to be a bit slower, but that's okay. Cool. So we load that up, and then notably do a .cache call here on it so that when we actually evaluate this thing, we will materialize a cache for it. And just to get a sense for the first few rows that we've got here. So you can see what we've got here is the title of the article as well as its ID, when this revision happened, as well as, some information about either the contributor ID and username, if it's a not anonymous user, or the contribute IP, if it is an anonymous user. Not worth worrying about too much right now. But what we do want to worry about is the text field here. So you can see here, this is just right now a long string of text in each of these that is marked up with a whole bunch of Wikipedia markup. So we're going to materialize the cache and get that going. So in this case, if you've been running through that graph frames notebook, you're definitely going to have some cache eviction issues, or if you have not restarted your cluster, as I didn't, you're going to have some cache eviction issues because this data frame is going to take up 1.9 gigabytes of memory once it's deserialized and loaded into memory from Parquet.
Question. So, if you keep caching, you might be running out of memory. So at that point, does Spark automatically switch or remove some of the previously cached files? Or?
Yeah. So the question is, if we do cache too much stuff to the point where we're hitting our memory limits, what we have allocated to in-memory storage, then yes, we will start to evict partition by partition data until we have enough space to load in the new partitions that we want to cache. So that is done on the partition level is kind of the important point there. So that's where the partitioning concerns come in. Cool. So that count finished running. You can see we have 111,000 articles here. And now that we've cached, that's going to be way faster. So once again, we're just setting up a table that we can query on using Spark SQL if we want to. So I'd recommend, as you're going through the exercises again, use whichever API here you're most comfortable with as you're playing around. So here we go. The first question we want to figure out here is how many days of data are present. So again, I like data frames, but we can take a minute to solve this one in whichever query language we want to use, or query DSL. Get that imported. One more thing I'll point out is that this last ref PDT time field is already in timestamp format for us. So we don't need to worry about formatting here. We just need to extract some information from the timestamp. Okay, so raise your hand if you attempted that one. Cool, got a few people. Yeah, so the way I did this was just selecting the last revised time, extracting the day of the year from that, with the feeling that, okay, we probably are only pulling this data from 1 year. Doing a distinct on the numbers that we get back, and then just showing that. So you can see here that we have 3 days worth of data. So there was someone asked me a question during lunch, which is how can I look up some of this stuff, or where are good references to go to after the class when I'm programming to figure out the particular functions I need to write. I think when I was going through these labs and kind of solving these questions before today, something I consistently did was look just through the Spark SQL function documentation that we looked at earlier. This is a really useful one for just getting a feel for all the functions that you can use in Spark SQL. Resource number 2 I would immediately call out would be these notebooks. Just going back through those, you can find especially for some of the useful patterns, like extracting a timestamp. If you've got that ISO 8601 format, we have a really easy hack in there to do that. The last place, just as an aside here, if you go back to the class document at the bottom, I started up a useful link section. So the Spark programming guide is actually really fantastic and pretty easy to read. So looking through that programming guide might be a good reference as well. For learning some of this stuff. Yeah, question?
Well, I was just going to add to the documentation comment you made. You really want to look at the classes and the objects.
Yeah.
That's very, very hard. Most people miss
Yeah, 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 yeah.
I used it for months, and it drove me crazy. There's classes, and then there's also corresponding objects with the same name that sometimes have all the functions you're actually using.
Yep, yep. Yeah, you need to be careful in the documentation here in terms of looking at the classes versus the particular objects. And all the details there. Cool. And yeah, actually, TAs, if you guys want to put in any more useful resources at the bottom of the reference sheet, in terms of just like, I want to look through documentation. I want other references for how to code well in Spark and what good practices are, that sort of thing. Programming Guide's the one I referenced here outside of the notebooks that we provided here. Cool. So again, you can use this day of year function in Spark SQL as well. No problem. This is that back and forth that we've been talking about that we really want to make sure is clear. Cool. So from here, we just want to figure out what percentage of our articles we're actually looking at. Right now, when we see about 2%, we're actually looking at, in this 3-day time span, about 2% of English Wikipedia has been edited. Kind of interesting. Cool. So we'll kind of blow through these. But the question is, how many of these articles were edited by cluebot-ng? So we can do that in SQL. Select. And what did we register this table as? Wikipedia. And then we want the number of articles that were edited by this anti-vandalism bot. And the column name we care about there is contributor username. cluebot-ng. So again, rather than do the filter, we just write this as a SQL statement. Oh, and we can display that. And we're meant to take a count here, so we can just do that really easily. So again, just as easy to do this in data frames as SQL. If you're following along, it will not then be too bad to just show the first 10 records here. And I think we all believe that that's going to work. And yeah, so if you're kind of interested in some of the Wikipedia anti-vandalism stuff, you can click into like particular revisions, that sort of thing, and it's kind of interesting to see what's going on there. So we can continue to query this for different, asking different questions about what editors look like, and here we're asking who are the most recent editors. Many of them are bots, but we can keep kind of running through this. And so then moving on, here's kind of our first text extraction question, where we're also going to, again, use a UDF. So the question we want to figure out is the titles of articles that contain a particular word or phrase. So what we do here is write a user-defined function. And this cell is going to be the same for the Python folks as well, because as mentioned here, UDF support is better on the Scala side. This has to do with serialization in JVMs, right? If we try to write Python-based UDFs, then we have a whole Python interpreter that we also have to run in order to make that UDF happen, right? So support on the Scala side is typically better, and it's much easier to write UDFs in Scala. So we do that here. And in particular, what this function is going to do is, it's not worth worrying here about the syntax or anything like this. We're basically just saying, can the word W be found in the long string S with a pretty standard regular expression match here, right? So we then register that function as word. Do a little bit of testing on that to make sure that these actually work the way they're supposed to. And here we have just kind of a cool feature in the Databricks UI. So here we've done this $word parameterized query with the SQL magic. Really nice. So we can actually look now for particular words inside of our data set, and we're going to have that filtering happen live. So if I type in NASA as it suggests, and again, this is a bit slower because we're using a UDF, number one, and then we're doing that full text matching, number two. And when possible, just as a reminder, you really want to avoid using UDFs. So we can see here, here's a whole bunch of articles that contain the word NASA in their text. And this is kind of a list of articles that we might expect, right? So now that we've done that, we've done a little bit of querying where we're doing some text matching, a very sort of janky full text search. Let's start thinking about using some more formalized tooling, right? And we can actually start thinking here about using some of Spark ML's feature extraction tools to pull out exactly what we want from this article data set and get it into the format that we want, right? So that we can proceed on to start talking about machine learning and how we're gonna apply a couple of algorithms here. So what I'm doing here is, first of all, as you can see, we're now using the some functionality from the Spark ML library. In particular, this is going to be something that tokenizes our string based on a particular regular expression we care about. So we instantiate one of those and then set some configuration options on it. You can see here that we actually set the columns on the data frame that we care about. So text is an input column that already exists, and words is going to be the column that we output to. And we'll see what that looks like in just a second. And for those of you who have seen, for example, scikit-learn's API, this is going to be a really familiar looking machine learning pipeline API. Actually, that's the question. Show of hands, who is familiar with machine learning pipelines in some other language? Cool, about half. So hopefully this interface looks really familiar to you in terms of having transformers, estimators, that sort of thing. So the first thing we're going to do is use this tokenizer, call our transform on the data frame of articles that we've been looking at. As you can see, this is going to be a transformation. It's lazy. It gives us back another data frame. And now we're actually going to trigger some jobs. You can see here that tokenizing was really quick, right? Oops, and that's because of some of the caching that we did. But let's only show what we care about. Oh, cool, that's what the next cell is doing. So you can see here that our words Our words column is now actually a sort of complex column type here. It's an array. So when we select off title and words and take a look at the first result here, we have one column, which is the article title, and the second column is that whole long list of words. So we're gonna continue with that, and we're gonna continue along this pipeline shortly, kind of as we move into the machine learning stuff. This is sort of a useful thing you can do. With a data frame, you can take a subsample of it. This is of course really useful like for train test split kind of stuff. However, there is plenty of tooling around train test splitting in the Spark ML library that you want to use. Or if we're just doing something exploratory, want to build a toy model quickly, we can always take a subsample, so that's going to train faster, right? So .sample function, really, really useful when you only need to work on a subset for whatever reason probably before you go up to production. You can even get smaller than the data that you're working on locally. So the reason we're going to use sampling here is because, as we'll see, so this actually should say articles here. We had 111,000 articles total, and now we're going to be looking at 11,000 articles. And in order to determine the most 15 common words in the English language, we need to look at our words column, right? Which again, just to show it off, is there. But notably, it is an array of string, right? It is an array of strings, right? So what we want to do is there's another function in that Spark SQL API, explode, which lets us say, okay, take every element from that array column and make it a row in a new, in this case, in just a new single column table. So what does that look like? Mm-hmm.
What's the first line import and then in the curly packages function?
Oh, sure. So there's a question about what is happening in this line. All we're doing, this is just a Scala syntax thing. So this is meant to be unambiguous because above we had asked you to import some Spark SQL functions if you were following along. This makes sure that we re-import those in an unambiguous way, and we alias functions to func, right? So that's just an alias that's going on. Similar in Python, we'd say like import SQL functions as whatever we want to call it. So then we then use that down here, the particular func alias, to call that explode SQL function. So you can see here we just now have a long list of words. This does contain repeats. But all those words from our 11,000 articles. So now we can see exactly how many words we do in fact have. Just looking at the 10% here. And that's 29 million words. So for the purposes, right, of trying to figure out the top 15 most common words in the English language, that's sort of more than enough to get a decent estimate there. So once we've done that subsampling and a bit of exploding into a table, we can just do a word count on this word list table that we've generated. So we do that. And end up with a table that looks like this. So in NLP, we call the sort of most common words that we see at the very top here, or at least some of them, we call these stop words. They're words that aren't particularly important to our analysis. So words like the, of, and, in. These words don't carry a lot of meaning, but are present everywhere. So one of the first things we're going to do in our analysis is actually filter out some of these most common words because we don't we don't get much from them in our modeling. There are a lot of them, and they don't have particularly any signal. So that's point one here. I think point number two is some of these HTTP title ref words. We don't think of those as stop words. Can anyone guess where those are coming from? Yeah, exactly. They're coming from the URLs. So the way this data looks, if we were to scroll way back up, I won't do so now, is actually these pages that we're looking at are marked up Wikipedia, which includes both the text we want to display for the link as well as the link itself. So there's a whole bunch of information like that that in a sort of more formal analysis, we would want to also make sure to strip that out in our data cleaning process, right? So we'll actually see that in action here. Another kind of feature extraction tool for NLP that SparkML provides is this stop words remover. So once we filter that out or create one of these removers and apply our transform call to that final data frame, you can see that a bunch of the previous words we saw, the, of, and, are all gone. So we're going to count up exactly how many stop words were in our initial table that we dropped out. You can see that by removing all those stop words, we've gone down from 29 to 23 or so. So that's a pretty big drop off, 7 million words that really weren't giving us any signal. Now, here's what happens when we do that top 15 count again without those stop words. And now you see this is probably the next step we take from here, right? Is kind of getting rid of some of these ref, HTTP, www, because I don't think we really think of these as the most common words in the English language, right? So we can kind of continue to work from there. And the last question we want to ask here is perhaps how many distinct words were here. And again, maybe we're missing some kind of markup language words that are still present. But you can see that there are about 718,000 distinct words in this sample that we took, which is a really large vocabulary. And as we'll talk about briefly, prevents a bit of a problem with machine learning that we're going to be able to work through with a little trick. Cool. So any questions there? Okay, great. Yeah, so we got about 45 more minutes here. And the next thing I want to do is, again, we're kind of moving into machine learning. So I want to just do a brief overview. It looked like on the survey, a large number of people were kind of familiar with the basics of machine learning, but I just wanted to quickly go through some very brief slides here that, first of all, overview some of the different tools we have in SparkML, and then talk about the particular algorithms we're going to be using in this pipeline that we're going to demonstrate. So you have an idea for what we're doing here, why we're doing it, what the impetus is. So again, if you've seen scikit-learns, hopefully SparkML looks fairly similar in terms of the way that this API and interface is set up, which is really nice for the Python API side of SparkML in particular. It feels really natural as someone who's coming from Python. So let me present this. I believe these slides are available in the, if you look on the class document, there is a Google Drive folder, and I believe the slides are in there. It's just one deck that I'm working from here. In any event, you can see on these slides some of the algorithm coverage we have. Kind of in the middle here is part one of doing machine learning, right? The feature extraction, feature engineering. Some of the linear algebra stuff over here is also really useful for that. And then part two is some of the modeling. So classification, regression, recommendations, clustering, all that kind of stuff. So these are distributed algorithms for doing all sorts of pretty typical machine learning tasks. And you can find more information about that in the documentation, that sort of thing. Yep, I guess the very last class of functionality that we really nicely get over here is some of this workflow stuff. So we can import and export models, and we'll see importing a model. And then we're able to save off those models once we've trained them, right, to put into production elsewhere. We've got pipelines again, so we're about to see what a pipeline looks like, because that's one of the really most useful things here, of course. And then of course we have cross-validation, grid search, all that good stuff. Yeah, so for those of you who are using older Spark, Spark.ml is the new data frames-based API for machine learning stuff. MLlib is at this point going out of style, so stick with SparkML on data frames. So with that all being said, kind of any quick questions there on, again, that really brief overview of the SparkML ecosystem? Cool. Hopefully that gives you a base point to kind of explore what features will be most interesting to you. So let's work through a demo of this on the Wikipedia dataset. So again, ultimately, what we're going to care about here is trying to topic model. So we're going to try to figure out, given the text of an article, what topic it is most closely associated with. And we're going to use a couple of very common algorithms here, TF-IDF and k-means clustering, in order to make that happen. So the first one here, TF-IDF. Show of hands, who is familiar with TF-IDF already? Cool, that's good. Again, about half. I'm assuming that's kind of the similar machine learner crowd. So the idea with term frequency, inverse document frequency at a very high level is, if we're looking at a collection of documents, for example, a collection of Wikipedia articles, each of those documents has a bunch of text, right, a bunch of words in them. And in particular, we can count up the frequency that any given word appears in an article. For example, we can count up the word the and see that the word the occurs 50 times in a given article. However, we want some way of determining the importance of that term in the document across the data set, right? So maybe a better word choice is cat, for example. And in an article about cats, the word cat is going to appear 50 times. In an article about World War II, the word cat is probably not going to appear. So what we want to do is basically say, across our entire corpus, across every single document that we have, let's count up how many documents actually contain this word. And so sort of for more meaningful words, if they appear more frequently in a given document, we can get a sense that that document might be about that thing, right? That's kind of the, again, super high level idea here. But we do that by taking our term frequency and then sort of dividing out by the number of times each word, or by the number of times that word appears across documents. So the easiest way to step through this is probably going to be a simple example here. So we have 3 Wikipedia articles. So we see that this one has a bunch of the and then politics and government. This one talks about politics and Congress, along with some of our stop words. And then last but not least, this article is talking about the Olympics, sports, games. So the first part of the equation here is getting our term frequencies. We count up that there are 2 instances of the here, 1 instance of everything else, and so on and so forth, 2 instances of Congress in this one. So from there, we just normalize by the total number of words in each document so that we don't have any kind of weighting issues. And now we're going to kind of move on to inverse document frequency. So you can see here why this is going to be important, right? We want to divide out basically by here the number of times we see each word in the article. So for words like the, they occur across every single document, right? So they're really not meaningful and not conveying much meaning to us inside of any of these documents. However, words like politics may be a little more interesting. They're occurring across 2, that sort of thing. So in particular, with TF-IDF, there are a bunch of different ways to compute the inverse document frequency. The most common one, and the one we're going to use here, is we're going to take the log of the total number of documents and then divide that out by the number of documents with a particular word in it. And then the very last thing we do here is multiply these 2 things together. But you can see how this is basically going to drop the score for some of our most common words to 0. So you can see here that the word the occurs in each of the 3 documents that we have. So that means its log is going to go to 0. Log of 1 is 0. And then from there, when we take our term frequency, the frequency of this term in any given document times the inverse document frequency, that score goes to 0. This word isn't very important, right? So this is actually kind of one of the reasons we can worry a little bit less maybe in this particular analysis about words like HTTP or image, because pretty much every article in English Wikipedia is going to have a couple of links. It's going to have a couple of images. So those TF-IDF scores for some of those most common words are still going to go to 0. So we get a little bit of sort of normalization out of this, which is nice. And then moving on, we can see the IDF scores for the other words here. And then across each document here, we're now computing the final TF-IDF scores, kind of as described. So we're multiplying the term frequency of the word government by the inverse document frequency. So again, this one appeared in 1 document, so we're taking the log of 3. And that's going to give us a pretty high score, right? Similarly for politics. And then looking over here, we see that the terms with slightly higher TF-IDF scores are in fact the terms that we really care about here. And some of these less important ones have had scores drop to 0. So already from this, we can start to get an idea for how we can use this in a machine learning context, right? Because we can take the scores for each of the words in a given document, put them into some kind of vector, right, as one does with machine learning, and start thinking about learning on that vector where scores are high, and then in particular clustering, right? We want to take clusters of documents where the scores for particular words are similarly high. Yeah, so TF-IDF is actually, if you've used Elasticsearch or other full text search things, this is like a very common Elasticsearch strategy for determining, if you type in the word cat, what documents are actually most important to the word cat, right? The ones where the TF-IDF score for cat is the highest. So in this case, we're searching for sports and politics. And can get back the appropriate results. Cool. So that's part 1 of the pipeline we're going to set up. And we can also take a look at the second part. So once we have those scores, again, we kind of want to cluster documents based on the scores for individual words, right? And then maybe that gives us some notion of what the different topics in our in our set of articles are. So the way you kind of always start doing this, if you're just setting up a simple pipeline, or the way you always think about starting to set up clustering is with k-means. So k-means is an unsupervised learning algorithm, and the way it's going to work is basically, or let's start with the end goal here, sorry. The end goal here is to basically take these articles about different topics and say, okay, these ones about countries should be in the sort of politics cluster, and these ones about sports should be in a sports cluster, right? That's what we'd like to see. Can we do that in a quote unquote unsupervised way just from looking at the text of the articles, right? So we have no notion of topic, no notion of anything pre-assigned here, or any kind of training data. This is completely unsupervised, and we're just trying to make some inference that, okay, maybe these articles are similarly grouped by topic, and these ones are also similarly grouped by topic. So in particular, with k-means clustering, the parameter that we have to choose that makes it a little bit tricky is k. So k is going to be the number of clusters that we actually want to divide our documents or our rows into. So in this case, we're going to try 100 clusters, 100 clusters to start out, just to see how it looks. And then, from there, you can kind of refine your analysis, try different values of k. This is one of those kind of tuning points and tweaking points in the machine learning flow that's made really easy by Spark ML. Cool. So the way k-means sort of works, and actually I have a YouTube video I want to show this. I think this is a really helpful thing. Is in this visualization, the blue dots are those cluster centers, and then the whitish dots are Wikipedia articles. So basically what we say is, and we're going to be doing this in a much higher dimensional vector space where we can't visualize things, but what we're going to be doing is saying everything, all articles that are closest to this particular centroid are going to be part of this cluster. Similarly for these, and that's what this partition is, right? So I think rather than kind of step through this, I will just show a video. So here's kind of what happens in the learning step, in the sometimes called the EM step of k-means. We basically have to initialize the cluster centers in a particular place, and then they start searching around based on a metric that we're going to set up of basically the distance, right? The distance in our vector space, the sum of all of the distances of the points to our centroids. We're trying to get the aggregate sum to basically be minimized. And it kind of looks something like this as the search process happens. We kind of iteratively, here, let me make this full screen, a little bit easier to see. We iterate over our data basically at each step, trying out different points and slowly moving along our cluster centroids until we find some kind of reasonable clustering where that aggregate, those distances are minimized, right? So this is kind of how this works. In this case, the data all seem to be sort of uniformly scattered, at least on the dimensions that we can see here. So we don't see anything particularly interesting, but we do see that k-means is quite good at setting up nice clusters on our data set, right? Like these are sort of very clear things. So that's kind of the process. Those centroids move around in the vector space that we set up, and we search through it. Cool. So from there, the next question becomes, how are we going to chain these two algorithms together, right? How are we actually going to take a whole bunch of TF-IDF scores from a given document, for all the words in a given document, and then cluster based on those scores and particular words. And the way we're basically going to do that is we're going to vectorize, right? So what we're going to do is we're going to encode each of our words as one column, basically. And hold on, there's a big asterisk here. As one column in a giant table, right? So maybe the first column here corresponds to cat, and the second column corresponds to dog, something like this. And then we're going to have basically really high-dimensional, many-column data set for each article, where each of these things, we call them features, right? Each of these words is its own feature. So now that I've sort of explained that encoding, can anyone tell me a problem with that? Or can anyone guess a problem with having? Yes, it is very, very wide. In machine learning, we call this the curse of dimensionality, right? So we just saw in our previous analysis that there are 720,000 words, and maybe we can filter out some of the like markup terms that we saw, that kind of thing. But we're still going to have far too many terms for a sort of reasonable column width, right? Based on the data that we have, we're just going to have too many features. It's going to slow things down. So what we're going to do is a bit of a hashing trick. So if we keep going through this, yeah. This is just kind of, again, explaining how some of this cluster iteration works, but I don't think it's particularly clear. We're going to, rather than take every word as a column, we're basically going to say, we need maybe around, for 700,000 words, 20,000 columns, not 700,000 columns. And we're going to hash every word into one of those 20,000 columns. So as we do that, and in particular, when I say words, I mean the TF-IDF scores, right? Again, basically our matrix is going to look something like this, where there's a column for each word, and then the value at each point in each row column is going to be the TF-IDF score. However, again, we have this huge problem, too many words. So what we're going to do is actually just hash down to 20,000 columns. This is going to tell us that, or I guess if we have 700,000 words and only 20,000 columns, what's the problem that comes up? We have collisions, right? Basically, there are going to be multiple words that go into each of those bins. And as it turns out, this isn't a huge problem. We don't worry about it too much. And so we kind of hash down, but the idea remains the same, where we're going to put the TDF-IDF scores basically in a whole bunch of different feature columns and cluster from there in this super, super high dimensional vector space. Cool. So that's kind of the pipeline that we're going to set up. So first, basically what we're going to need to do is, maybe I'll show this off first. First, what we're going to need to do is take our raw data frame, the one we were just looking at in the NLP notebook. We're going to take our raw, just Wikipedia text. We're going to tokenize it. We're going to get rid of those stop words. Those were the first two steps we saw in the NLP notebook, right? From there, we're going to do this hashing trick. So we have a nice hashing transformer in the Spark ML lib that's going to say, okay, for each one of these words, we're going to, excuse me, this is hashing term frequency. We're going to hash each of our terms into one of 20,000 buckets and compute the term frequency in each of those 20,000 buckets. From there, we're going to compute the inverse document frequency for each of those buckets using sort of an IDF step. From there, we normalize each of the vectors of IDF scores that we have, and we'll talk about why that is for a second. That just means making sure everything sums to 1, not too concerning. And from there, we perform our k-means clustering. Cool, and that's what this is going to look like in the actual notebook that we kind of run through here. All right, so very last thing in these slides is just the pipeline and what it kind of looks like. So pipelines are set up as these kind of chainable structures, like we just saw in the other diagram. And in particular, we have transformers, which are going to take one data frame, transform it into another. So this happens in a bunch of situations. It could be once we have a fully built model and we want to run a prediction with that model. For example, maybe we have a new Wikipedia article and want to see what cluster it's going to go into. That model is going to be a transformer that actually runs us basically from one end of this pipeline to the other, right? Where instead of performing the k-means training, we're instead going to, this time, figure out what cluster this belongs to based on the training we've already done, based on the cluster centers that we've already found. Transformers also are what we're using in order to kind of keep, throughout the middle of that pipeline, first extract all of our words, and then remove stop words, and so on and so forth. That's transforming from one data frame to the next data frame in our kind of feature extraction learning pipe flow, right? And then the other thing we get that's kind of nice is estimators. Once we have one of these full pipelines built, we can call an estimator's fit function to train our model on that data and produce, or train our model on that data to produce the fully built set of parameters that we're going to need for whatever particular model we're using. Cool. So that's the high level setup, and let's just dive back right into the notebooks. So this is actually an interesting notebook, and I kind of like the way this one's set up because we get to see the Python and Scala cells right next to each other. So you'll find this notebook in the Exploring Wikipedia folder in the very top level. It's not inside of Python or Scala. It's just right here, 09 dswikiml. So basically, what we're just going to do now is really quickly run through this exact pipeline I described and see if we get any interesting information out of this k-means clustering of our documents. So you can see here in the Databricks notebook that we have actually 2 copies of many of the same cells. So first of all, we have this one written in Scala, and you can see, again, it's identical in Python, but this Python magic is indicating to us that this is a Python cell, or this is a PySpark cell in particular. We're running the Python interface, excuse me, here to the Spark API. So basically, you can run whichever set of cells, again, you're more comfortable with. I will continue with the Scala cells. So again, we're just loading in that same data set we were looking at. We can kind of skip through these. So maybe the very first step that we didn't even show in that pipeline was just lowercasing all of the words in our data frame. So we just used the lower Spark SQL function to do that on the text column. And in particular, you can kind of see here what's going on. We select all the columns, and then we're actually adding in a new column, this is kind of a fancy way of doing that. There's also a .with column call, which is what I typically use to create a new column. So we can just see what the output looks like there. Maybe this isn't the best place to do so, but you can kind of see info box ship is capitalized here, lowercase in the final column. Cool. So from there, let's just set up this pipeline. What we've got here is we're just importing all of the different transformers that we're going to be using. And again, this is the exact same stuff that we saw in the NLP notebook just a second ago, just tokenizing this based looking for words in our regular expressions. This is probably the step we'd want to clean up if we were thinking about getting rid of some of those other HTTP-related words. Moving right along here. We're now going to, again, just do the stop words remover, just like we saw in the previous notebook, where, again, the way we set up these transformers is we set the input column that we're going to be operating on, and then the output column that we want our transform data to be emitted to. And then we can see what that ultimately looks like without stop words. We still have this sort of complex column type, an array of strings. So you can see how this transformation is kind of coming along. From there, we're going to get our term frequencies, again, using that hashing trick I was talking about. So this is going to, again, take all of our words, place them in one of 20,000 bins based on a hash function. You can see here that we actually determine how many bins we're using with the set num features call. And then increment and decrement frequencies as we see words in those particular bins. As we go along.
Other things besides term frequency?
I'm
guessing not. Depends on term frequency.
Right.
Are there similar things to reduce the feature set?
Yeah, the hashing trick is very frequently a trick that we use to lower down our feature space. There's also support for sparse vectors in SparkML, so that can also be an option. So moving along. Again, this is just kind of showing at each step what's going on, but I kind of want to speed through just setting up this whole pipeline here. So again, the next step in that pipeline is going to be now computing the inverse document frequencies based on our 20,000 hashed term frequency columns. So the input there is then going to be the hashing TF result, and the output is going to be the inverse document frequency. So this one does take a second because we have to scan over all of our documents. Right, so from here, the next step we're going to do is, again, normalization. So again, the very high level idea here is we just need to scale our data. And each of those vectors that we're thinking about as a feature that again, basically is all the text in a given article, we need to make sure that all gets normalized and scaled so nothing gets like particularly egregiously weighted. And we're basically working on the same, all in the same space, which is where every vector is of distance 1 from the origin. And this is kind of like a very common answer to a lot of machine learning questions, right? Did you normalize your features? Did you cross-validate? Those are the big two. So this one is going to take a moment here. That's fine. Any questions so far?
This hashing feature does not remove any data.
Yes, hashing a feature does. We lose some information, right? We can't do a backwards lookup.
Yeah, you can't get any inverse. But I mean, if you go back to the original space, we had this really wide set.
Yep.
Quite a lot of those were 0 because that word didn't appear in that article. So
Yep.
you're just removing the zeros,
Right, right.
You're not really, like, you're not taking away from the validity of what you're learning.
Yeah, the question is, are we taking away from the validity of what we're doing by hashing down like that? And the answer is no, models perform just as well.
I have a question.
stage did we remove, we did the multiplication to remove the words which are not needed or.
Oh, sure. The question is, so we're kind of moving along and doing the term frequency calculation, and now we're doing IDF. And the question is, where did we actually remove stop words? Is that your question?
Yeah.
Yep. So that was just a little bit farther up. Here we set up this stop words remover transformer where we set the input column and the output column, and we kind of keep going from there. Okay, well this one seems to be taking a moment to run. Okay, well, in any event, in the interest of time, I think hopefully you're starting to get a feel for how this interface looks and the way that we set up. Again, it's pretty standardized and common for each of these. We instantiate our transformer, and again, if there are parameters that we need to pass in, we're going to pass those in with that instantiation. Set the column that we're going to be doing that we want our transformer to input on. There could be multiple columns there too for some transformers, and then we're going to set the name of the output column that we want. Last but not least, you can see here that in our normalization step, this is, I guess, the Python version, but again, exactly the same. We're going to, output to a features column that we're going to then say k-means, use this long array of features to cluster in, to train in. And then the prediction column, so this is slightly different because k-means is an estimator. We're going to have those prediction values output to prediction. We're setting our k parameter this way to 100. And then setting the seed, basically, so when we initialize our centroids in our k-means cluster, we typically put them randomly for better performance. This is just a seed value so this is going to run the same way on everyone's machines. And then I think the very last important thing here, as far as understanding this pipeline goes, is that what we do to get a pipeline to work is we, first of all, want to import the SparkML pipeline object, and from there, we basically say, okay, I want to be able to reproduce this every time that I get some new data to come in, right? And in particular, I want to, again, just like we saw in that diagram, on one end, just pass in some raw Wikipedia articles, and depending on whether I call fit or predict or transform, depending on which of those I call, I want to train my model, get predictions on my model, and so on and so forth. And we can do that all in the same pipeline, right? So that's a really, really clean interface that just makes life a lot easier in terms of developing these models. So the way that we specify the pipeline, and note that this is an array here, so it's going to be in order, is first we're going to use the regular expression tokenizer that we defined above. Then we remove the stop words. We compute our term frequency and do the hashing trick. We then compute inverse document frequency from those 20,000 columns. We normalize our features down to distance 1 for everything, and then perform k-means on it. So let's see how this stuff is all running. Okay, great. So then we can run this, nothing's going to happen. The final step here, which would take a long time on this data set, would be if we were to call then, we can just call pipeline.fit, again, on this very initial data frame where all we did was lowercase, right? And we could even put lowercasing in as part of our pipeline if we wanted to. Yep. Yeah, so question is how do we then save this model? And that's very easy to do. once we call fit, there's a model.save function, and you can write that out to wherever you need to, which is a great segue into this next step, which is where we're calling from the Spark ML pipeline model interface, we're calling .load to load up the sort of pre-baked version of this model that we've already saved off. So this one, I think, takes a minute as well. This is going to trigger like a ton of jobs.
So some customers follow more on a different platform. So in that case, all that is standard synchronized platform for all.
Yes, so the question is, what if we want to train a model here and then export it to somewhere else? So I believe Spark is working on supporting PMML, which is kind of the unified interface typically. There's some support there. TAs, do you guys know exactly how much support there is right now for PMML? Most models are good there? Yeah, so you are able to export to a common format to then load it up in whatever production environment you want to use. Cool. So that wasn't too bad, and we're just coming up on the breaks. This is going to be perfect. So from here, what we can do is, now that we've actually done our clustering, right, we can see what clusters each of our articles got placed into. So we can see here that whole pipeline has been run. There's lower text, there's words, no stop words, hashing, TF, IDF, features, and prediction. And then when we actually call this pipeline on a few of our articles, cool. We'll get something that looks like this. All right, so we're coming up on 3:30 now. Any last questions here on this machine learning stuff? Cool, feel free to put anything else you have into the document. Always welcome more questions. We're maybe 15 minutes behind where I thought we'd be. That's totally fine. We'll take a break for the next half hour until 4 p.m. and then just spend the last hour on Spark streaming. And the two APIs that exist for that right now. Oof. Hey.
When everybody comes back, first thing you
Survey.
do is
Yeah, 100%. Yeah, definitely my plan. Yeah.
Okay, cool. Just
Yep.
double check.
Yeah, I'd love to actually.
The slides is not shared to us. I didn't see any link in
Oh, the slides aren't shared? Okay, I'll ask the TAs about that and we can look into it. Hey, Brian, I just wanted to check with you. Any feedback for me in particular on how things are going? Or?
Now, let's take a look at this survey and then we'll talk. I think any feedback I might have at this stage in the game is kind of irrelevant since we're almost done.
Yeah, sure.
What would be better is to plan to take the feedback that you get from the class, and then we'll sit down and we'll talk about it. And I do have a few suggestions for you.
Okay,
Let's
cool.
do it in the context of the feedback.
With the feedback, sure. Yeah, that sounds good.
And so we can do that. Are you staying for the whole conference, or are you taking off?
Yeah, I'll be here for a couple days after this. Yeah.
Okay, so we could do it sometime this week before we both fly out.
That sounds great. Yeah.
Okay.
All right. Cool. Thanks, Brian.
Yep.
All right, guys. It's 4 o'clock. Excuse me. It's 4 o'clock here, so I think it's time to get back to it. So we have about 1 hour left. I hope you've enjoyed everything so far and found it interesting. Like I said, for this last hour, we're going to talk about Spark streaming here. But first, there's one really important thing that I would like everyone to do. We try to get basically 95% completion on our post-class survey. Your feedback is really, really important to us. It helps us shape what this class is going to look like in the future. We want to make sure that you enjoy the class and can kind of go from there in terms of improvement. So we would really, really appreciate it if everyone just took 5 minutes right now to fill out that survey. You can find it on the student reference sheet here, which again, that's the tiny URL is right here. You can just scroll down to the post-class survey. Yeah, so please feel free to share anything you liked about the class, any comments, any suggestions for improvement, whatever those may be. And let's just take 5 minutes here. All right, cool. So has everyone completed the survey? Does anyone need a minute? Has anyone not completed the survey? If you haven't, please do so. Again, really, really important to us to get that feedback, and it means a lot. But I don't want to spend too much more time thinking about that there. It really just takes 2 minutes though. So yeah, so to start out, kind of talking about Spark streaming, we just want to give a quick overview of the architecture that we're going to see here, talk about why some of the design decisions were made, and what everything looks like here. So in particular, some of you might be familiar with Apache Flume or other streaming technologies that allow for live sort of stream-based ingestion, right? Spark uses a different model. Spark uses micro-batching. So let's take a look at what that actually looks like. Basically, the idea here is we are going to collect data for some fixed period of time, and it's micro, so we typically make that interval of time fairly small, on the order of seconds. We ingest that data, and then once we have a batch of data, we run some process on that batch of data, right, or on that micro batch. So the sort of rationale there is we can get a bit more stability out of this, and we can also, as we're going to see, especially in structured streaming, start to think about getting better consistency guarantees, which is nice. But the sort of main stability condition we have to worry about is that as our batches come in, so basically the way this is going to work, right, is if we start our stream here at time equals 0, we collect 2 seconds worth of data, and then this first processing job is going to run, right? If this first processing job takes more than 2 seconds, we're going to start experiencing backup problems, right? Where this takes too long to run. That means we're collecting in more data. We start running into memory errors. We start running into timeout errors, and it gets really messy, right? So the main thing we have to think about in terms of stability in microbatching is that we don't do anything too complex or anything that's going to take longer to run on our data that we've ingested than the window interval we've set. So as we'll see, we can think about kind of tuning that window interval, that batch interval. Window interval is sort of different. Tuning that batch interval to make sure that we have enough time to run the particular processing that we want to run, making sure that window's not too small, that we're going to run into issues there. So on the other side, this is kind of what an unstable operation would look like, right? Where it takes us, upon receiving our first unit of data at 2 seconds. If it then takes 2.1 seconds to process that, we're going to start running into issues, just collecting too much data, again, trying to load too much data into memory, and that becomes very unstable. So in order to demo some of this functionality with Spark Streaming, we're going to be looking at, again, Wikipedia, English Wikipedia edit streams in particular. You can see here we actually have servers set up for English, German, French, Russian, Italian. But the one that we're most interested in here is going to be English, and we'll just work on that. If you do want to change the port numbers, you can mess around with the different Wikipedia edit streams. English is also the one that's most frequently edited, so we'll have the most data coming in from these streams. Cool. So that's the very high-level idea. We have these batches. So how does this actually look in a sort of step-by-step process? Here's what's going on. So the idea here is this is our executor JVM, right? And we have some number of cores in that executor. In the case of, we'll see an example where this isn't necessarily the case, but for many sources of data that we're going to be ingesting streams from, we have to dedicate one core to being the receiver core. So that's the core that's going to take that second, and during that second time interval, just be ingesting data and turning it into, in the case of Spark Streaming, an RDD that we're going to be able to use. Processing, I guess, with our other cores, right? So the main point there, we do have to dedicate a core, the receiver core, to doing that. So the idea with this slide is this is our Wikipedia source. Our first 200 millisecond window of data comes in. And at every 200 milliseconds, basically, we're materializing a new partition inside of our RDD that can then be sent out to each of these cores. And so both this batch interval and the window interval here, these are both tunable. But you can see 3 partitions, 200 milliseconds across each. So this batch, right? So after 600 milliseconds, we have one RDD, 3 partitions that we're going to be able to process. On the data ingestion front, the same thing keeps happening, right? So there's now another 600 milliseconds of data that comes in that materializes into the second RDD, and so on and so forth. So we have that streaming ingestion happening. Each of our blocks comes in. And then the RDD that was just materialized based on that incoming stream data is then converted into or passed to the API, to the end user, as something called a dstream object, which is going to look reasonably similar to an RDD, and we'll take a look at that interface momentarily. And then from there, we can call a few operations on it. We can call filter. We can call a for each RDD operation. We can set up windows. We can do a whole bunch of stuff that we're gonna take a look at. So that's happening in one dimension, right? Is all the data processing for that first batch we received. And then in the second dimension here, as we were just talking about, we still have new batches being created and being queued for processing, right? So you can see as those batches build up, if this dimension here going down takes longer than 600 milliseconds, we're gonna have some serious backup issues, right? So we can also consume from multiple sources, again with the caveat that each source we consume from requires its own core. And as this happens, we receive two sort of micro batches in parallel that we can then sort of join up on, we can process on, things like this. So this is one of the powerful points, right, with Spark Streaming, is that we can join multiple data sources together. We could look at multiple edit streams. We could join up edit streams with any other data that we were particularly interested in joining it up with. It's maybe a static RDD, anything like that, write it back out to a table or whatever else we want to do. So again, the dstream API, like I said, fairly similar to the RDD API, which means that the transformations that we see are going to map from one RDD to another RDD. We haven't really talked much about RDDs today, but I do want to kind of show off just a little bit here of what some of those looks like. So some of the most important transformations when we're using the RDD style API are map, filter, flat map, kind of functional programming constructs that we just don't have a ton of time to discuss today, but are important. And I think this is more or less the end of this deck here. Yep. So yeah, I guess one last point that we can see here is most sources that we're going to be ingesting data from, such as the TCP streams that our Wikipedia edit data is coming in from for this first example that we're about to look at, those all require one core as a receiver. In the case of Kafka, we actually can set up a receiver, what's called a receiverless source. So we don't dedicate one core to ingesting data from Kafka, and instead we query out to Kafka to say, hey, give me this batch of data, get it back from whatever topic you're subscribed to, and kind of go from there. So just a little aside, kind of on Kafka and that it is useful. Yep, and then I think very last thing here, these slides are a bit dated, so the next ones kind of talk about structured streaming, which we'll get into. But also there are a few online machine learning type algorithms we can do, which is kind of cool with our D streams. We can do regressions, we can do k-means in an online manner, so we're kind of updating our clusters as more data comes in. So just kind of cool. Unfortunately, in Spark streaming, you do have to use that MLlib API, which is, again, a little bit falling out of style, but it's in maintenance mode. Cool. So any questions there? Yep.
Is one of those models kind of push and the other one's pull? Is that your way to describe it?
With the receiverless source, I believe so, yes, because we are able to query Kafka.
And the other one's making a connection that's
Right,
pushing at it?
right. And this is because Kafka has this sort of like replayability where we can just pull back from recent time. Cool. Okay, so the first notebook we're going to look at here is number 10. The streaming student, and this is just going to be a nice first introduction here to what's going on with some of the Spark streaming. Again, we are going to see the RDD API, which we haven't talked a ton about. But that's sort of an API that I don't think should be too much trouble to see here, so that we can get this overview of what's going on with streaming. Cool. So what we're doing here is setting up a couple of constants. We're just setting up the particular port and Wikipedia host we're going to consume from. We are setting our batch interval. We're going to look in 15-second intervals at this data. And then here we go. So again, we're using the kind of old school RDD based API. So we have to we pass in here a Spark context, which we don't use as much in Spark 2 anymore, but we use here for Spark streaming, along with the particular interval of batch that we want to come in, right? So once we're there, once we have our streaming context initialized, we're just going to connect into our server that's dumping out Wikipedia edits line by line and in this live manner. So this is just a TCP socket that's kind of dumping data down to us. So here's where we start to see some of the dstream API, and in particular some of the kind of functional constructs that go into mapping and doing operations across each RDD that comes in. So again, you think about the dstream, right, as something that's giving us RDDs in time, right? So what we're going to say is, for each of those RDDs, if it is not empty, we're actually, and this is a little bit tricky, right? We are actually going to create a data frame from that RDD that we can then query on. So why are we making a data frame from this RDD information that's coming in? The idea is just so that we can see what's going on, so we can get a feel for how this is looking under the hood. But you can imagine, this is the section where you can do any sort of operation on the RDD that you want to do, any kind of transformations, aggregations that fit within our 15-second window. And then this streaming context remember thing is again just another internal point so that we can keep track, or so that rather our table isn't evicted in the minute time frame, so we can keep looking at it even as more data comes in. So each time here, so I guess one note is that this function is going to happen for each RDD, right? Which means that each RDD that comes in is going to again create a new table. And in particular, each time we're just going to replace that temp view all edits with the new table that we're looking at, right? So we're using the replace portion of this create or replace here after the very first time. So just a few seconds ago, I hit the streaming context.start. So this is actually starting up our streaming job. And I believe it's been 15 seconds. Yep, so that table has been registered because we waited 15 seconds to try to select anything from it. So here we go. We can see some live data that's coming in, this live JSON data from Wikipedia. And we can see all the fields that exist in there. And here, oops, this is just showing us which language Wikipedias are coming in. I guess while that is the English stream, we do see some we do see actually all languages on this stream. So that might be a bit of a misnomer on port 9002. In any event, not too important here. So we do a little bit of date formatting again, just like we were before. So we can take a look at what's going on a by-second basis. And then count up how many edits are happening in this window, in this batch interval of time, right, that we save to a table. So the way this is running, again, is this data gets ingested, written to a table, and each time that happens, that table is replaced with the new view. But we can still query on whatever the most recent bit of information, or whatever the most recent batch of information to come in was, right? So that's what we do when we run each of these cells, just so we can take a look at what's going on here. And from here, you could imagine kind of turning something like this into some sort of dashboard, right? We ingest the data, we put it into a table with the live information for any given minute, and then for any given 15-second interval, and every 15 seconds, that dashboard updates its information based on the newest stuff that's come in, basically by querying from this table. Cool. So any kind of questions there on what this looks like in Spark streaming and how we ingest data, kind of map a little bit? Yes?
Can you explain the remember function and what exactly does it do?
Sure. So all that's doing is just making sure that that we have a 1-minute buffer on the data that's coming in, because of the fact that what we do here is every 15 seconds a new data frame comes in, we ingest it. So basically, the thing we're trying to guard against is in that 15-second window, somehow that memory that is allocated to that RDD from 15 seconds ago being eliminated, right? From that all being evicted because new data is coming in. So just by setting a 1-minute remember time, although this table is updated every 15 seconds, we're just trying to keep ourselves clear there.
So what actually happens? The table contains 1 minute of data?
No, so this does not mean that the table contains 1 minute of data. It just means that the underlying RDD that the table is drawing from is kept around. Each of those RDDs is kept around for 1 minute at least.
Oh, so it's like caching.
Yep, exactly. Mhm.
So now we are getting the latest data, but if we want to keep the old data, the meta-analysis and aggregation, how do we-
Yes, so the question is, what if we want, so right now we're just getting the latest data, looking at it, and the question is, what if we want to do some aggregation save off? Yeah, that's a great question, and there, for example, that's an action we could call inside of here, right? We could actually just save off this data here instead to some other table, and maybe we could be appending to a table, that sort of thing. And actually, we're going to see with the structured streaming API, this becomes a whole lot easier to reason about. Cool. So now we're going to switch over to notebook number 11, which is just showing off some of the sliding window functionality that we get in base Spark streaming. So if we switch over there and do the imports, what we're trying to do here, right, is show off, as all this data comes in, let's look at every 5-minute window. Updating, it's going to be, I think we keep our batch interval at 15 seconds here. We'll look in a moment. But how many edits occur across that 5-minute window versus another language? And so this is kind of, again, just showing off that we have the ability to look at windows in streaming, and then there's also going to be some implicit remembering that happens there as Spark streaming just takes care of all of the internals of windowing for us, which is nice. So we actually do a 1-second batch interval. So again, pretty much all the same boilerplate here for turning on our streaming context. So again, here's what we're going to do in terms of turning on the window. We're going to set a 2-minute duration for this window, right? And I think our batch interval is actually 1 second. I'm a little bit concerned about that 1 second time. So if you're following along, what I would recommend doing is changing this to 15 seconds if that's not the case in your notebook. So just set that batch interval at the top to 15 seconds and rerun that cell. So again, going back down here, we then set up a 2-minute window that we're going to look at. So in this case, you can see what we do here is now our stream is going to keep track of the past 2 minutes worth of data. We then do this coalesce where we move each window down into one, excuse me, each batch down into one partition. I wouldn't worry too much about that. And then we basically set up the same table, right? But this time, we're just going to set it up over a window. So we're going to see this table grow for about 2 minutes, and then after 2 minutes, that table is just going to update every 15 seconds with the new 2-minute window. So again, we just give ourselves a few minutes. This time we're just giving ourselves a few minutes of buffer time. Oops, I must have forgotten to kill the other streaming context. If you see the error message that I just saw when I ran this ssc.start, you can go down to the very bottom of the notebook, run this cell, which is going to stop all the streaming contexts that are currently active. You can only have one running at a time inside of a given Spark context. Cool, there we go. So now we are collecting data. And actually, this is kind of interesting. I just started that a couple of seconds ago. Did the batch interval not change? Or did I actually run that for longer than 15 seconds? Oh, I think you're right. Thank you. Yep, I forgot to reset the streaming context. I guess we're okay at a 1 second batch or below. It seems like we're able to aggregate and count data here. But you can see as this table grows and grows over our 2-minute window for each of those second intervals. So now our window is just going to be sliding along a second, right? As our window grows and grows, we see more edits come in, and then eventually this is going to start to stabilize out. And then we can actually take a look at what's inside of that table. And then again, we're just doing this group by operation. And just some very similar aggregations on that table. So this is a pretty cool point here because we're ingesting data every second, right? And what we're doing here is grouping by our timestamp. We can see how many edits came in at every second inside of our window. And we can see that that currently ranges from 1547 to 1407. So we haven't actually finished that 2-minute windowing yet. But if we go back. So now the start of our window is 1427. And the end of our window is 1627. So we're just sliding along that 2-minute window now, keeping track of what's going on. So we're saving off a little more state here. So that's a little bit on the windowing functionality that we have. And then you can think about doing aggregations across those windows and this sort of thing. Sorry, what was that question?
Is that possible to batch the data based on processing time?
Is it possible to batch the data based on the time at which we process that, we receive and process that data?
Yeah, we can skip some data.
That's a good question. I'll throw that one back to the TAs. Are we able to load in the timestamp of exactly when we receive the data? We could keep a running clock going for sure, and that might be the way to do it.
Works off of, original Spark Streamer works off of the processing time. It doesn't do event time.
Oh, okay, yeah.
Yeah, the processing.
Right. So we're always going to be working on receipt time. And so, yeah, we're actually going to see there's a distinction between event time and receipt time in Spark structured streaming. But in terms of just keeping track of that, I think we can just do that with some kind of timer, right? And in terms of what the current time right then is. And the data that we're going to be receiving in, if it has its own event time, is going to be just a separate notion, right? Cool. So any last questions there? Yep.
So when we were working with data frames before, we had to be kind of explicit about when we wanted to keep it in memory and when we wanted it to be on disk. When we're streaming in and creating these little micro batch RTDs, are they always kept in memory? And is that going to pose a problem? Is there anything you have to tune for that?
Sure. So the question is, are all of these micro batches going to be kept in memory? How does the kind of memory, what is the memory setup like here in a sort of regular Spark streaming? And the answer to that is we are going to, yes, we're going to, for the most part, keep batches of data that are coming in immediately in memory, as well as much as we need for the particular window that we maybe care about. After that, no, we start, and this is why we're using that ssc.remember call to keep some of that data around in case those batches get dropped off. Because anything from outside of that window in the case of Spark streaming, we're not going to need to worry about. And then, of course, on the other side, we probably start thinking about saving off whatever computations we're doing to disk or some other persistent data store, right, to keep track of what's going on. Cool. All right. So it's 4:35 now. We've got about 25 more minutes here. So I think the last thing that we'll have time to talk about here is going to be the structured streaming demo that we've got for you. So one last point on regular Spark streaming is we just have this nice, slightly more involved lab here that, again, just shows off connecting to a receiverless Kafka source, as well as some slightly more complex aggregations and things like this we can do with the base Spark streaming API. Cool. But that being said, let's talk about structured streaming, how it looks, how it works, how it makes our lives a lot easier, and why everyone's really excited about this. So at a very high level, we saw that in regular Spark streaming, we have these batches of data that each one is an RDD, and possibly we window over some time frame. But that's effectively what we're working with, and we kind of have to do our own reasoning from there. The sort of goal with structured streaming is to take that micro-batching model and somehow find a way to make it work with data frames, right? So there's a question of how does that work conceptually, how does that work in implementation, and these were a whole bunch of problems that have sort of been worked out into the following framework. So the way we're going to think about our data stream as it comes in with Spark structured streaming is we're going to think about it as this unbounded table. So it's just a giant data frame where new rows are constantly being appended, right? And the way this works under the hood is still micro-batching. It's still batches being appended, but this is the sort of way to reason about it. So in the case of Spark structured streaming, we call that interval the trigger interval, where in some interval, data is appended to that table at any given time. So the next step then is once we've received our data, which you can see here, we're looking at, again, the x-axis is going to be the time dimension here. So at time equals 1, we receive some amount of data into our table. We then call some kind of result aggregation on it. And typically, you'll see what we do is we can either keep track of running aggregations or some window of time or a number of things. We definitely do want to worry about our input table growing too large and needing to keep track of all of that state. So we do have to be careful sort of thinking about that. Yep, question? Oh. Okay, cool. Yeah, feel free to put it on the doc too. But in any event, we can think about this table conceptually as as continuing to grow. Whether or not that's actually the case depends on the implementation, the sort of queries we're running, and how much data we can get away with getting rid of. We definitely don't want that to just be constantly growing in an unbounded way. Then from there, we run our query, we run our aggregation, and we have some result table that goes out, right? Or that we get based on that aggregation. So that's kind of step 2. We run our query. Now in Spark structured streaming, there is an explicit third step, which is the output. So we basically write this result table to some given output. We call them output sinks. So those we'll take a look at what some of those things can be. But there are any number of different places we can write to an in-memory table for debugging. We can write out to files like columnar file storage formats. We can set up our own. We could make a JDBC connection, for example, to connect to some other database where we're storing aggregations, things like this. So, yep, there's a question?
How is it different from
So the question is, how is structured streaming different than just the previous streaming model we were looking at? Well, this time we're using data frames, right? Which is really nice. And previously we were thinking about each individual, so we can set up a sliding window of separate RDDs where that becomes one window of information. However, what's different about this, as you'll see, is we just think of this as one single long data frame. We don't have to worry about windowing just up front the way we do in regular Spark streaming. We just have this one long input table that we think of as continuing to grow, and we're probably going to window over it, but we can really do anything we want to that unbounded input, to that input table. So I think the main niceness here is that it's now explicitly a table, and the reasoning is a bit simpler. Is there another question?
Would you ever go use that older one? This is the new version. Would you ever go and use the older one?
Sure. So the question is, why would you go and use RDD-based Spark streaming? That's because structured streaming is currently in alpha. So it's new functionality. I don't know too much about the timeline, but it is new. So that's why we're kind of introducing both here.
Yeah, just to jump on this structured streaming. So we're aiming to sort of GA, or Databricks is, or the Apache Foundation is aiming to GA it in Spark 2.3. So we're on 2.1 right now, and 2.2 is coming out probably like next month or something like that. So if you're going to build something now, so Databricks internally runs structured streaming and runs production workloads with structured streaming. So if you're going to build something now, we would really recommend that you build something with structured streaming, especially if it's sort of greenfield. It's got a lot of advantages, just sort of being able to do event time. We're moving towards sort of complex event time, and some pieces are there to be able to do that. So it provides much more flexibility and it's a little bit more robust.
Cool. And one more question, yeah?
Yeah, I still didn't understand the advantage of structured streaming, given that the internal RDDs are really not stored, right? As soon as your window is completed, RDD is removed out of memory, which means that in reality, your queries run only upon the current batch, and then your results are somehow appended back to the earlier result, and not that the queries run on the complete data frame.
Right.
So how is it any different from me doing a streaming and then appending the results myself instead of using structured streaming?
Sure. So the question is, how is this any different than just appending all my results to a single table that actually is unbounded and growing? We'll see that typically when we're doing aggregations here, while we think about this as an unbounded table, this is not actually going to be an unbounded table. So structured streaming takes care of that dropping off for us over time based on what we need to run our current aggregation and query. So we'll see a couple examples of that in just a second. But basically what Spark structured streaming is giving us is a lot of structure and guarantees and again, this really easy interface. So kind of moving along those lines, here are some of those output syncs that are currently supported. Probably the two most salient ones right now are file and for each. So right now we can only you can take that result table and write it out to a file. But right now that's only supporting Parquet. So if you want to implement something custom as of now, you would use the .for each. Console and memory output syncs are of course mostly useful for internal debugging. Then from there, the next point here is how we're actually writing out that output table. And this basically we have a couple of options here, where in one mode we can actually write out the entire result table after every batch interval here. And if we do that, basically each time the table is going to be written out to the sink as its own new full table, right? We can also do an append, which is a little bit cleaner, so then we just have one result table that we're maybe appending results to, or or this sort of thing. So basically, you can use append typically if we are collecting, maybe for example, the example we're gonna look at below is looking at some log data. Maybe we want a table that's parsing in the huge amount of log information we're getting, right? And only outputting errors to some database table that we care about, outputting errors that we care about to some database table. In that situation, we might think about using append, right? Because we just append our error messages into that database. There aren't going to be nearly as many records as there are all logs, but those are ones we particularly want to see. Whereas in the case of complete output, maybe we think about rewriting the table each time if, for example, we're updating a finite set of values with counts that are coming in, something like this, if we're taking some kind of aggregation along those lines. Mm-hmm. So there's a question which is, in complete output, is the previous data lost? And I think it depends on the implementation of the individual sync. But in general, I want to say no. That's a good question for the document in the TAs. Cool. So let's take a look at how this is sort of different here in terms of the creation that we're doing. So the first thing we do here, again, just set some constants. So here's the code that we're going to be using actually to read in a stream for the purposes of structured streaming. So you can see we do spark.readStream. So we're back in the Spark, in the sort of Spark world rather than going back to the Spark SC Spark context. We are going to be reading in from a socket, and we'll talk about this in a moment, but there are some concerns around reading from a socket and some of the guarantees that we can get out of Spark streaming. Reading data in from a socket doesn't allow for those nice guarantees that are one of the most powerful parts of Spark structured streaming. In terms of redundancy and completeness, we don't drop any data. But in any event, we can run this cell in order to just start up a simple structured stream on this socket so we can get a look at what's going on. So you can see we just have a single string value column here. We don't know what's coming in, right? We just know that we're consuming from a TCP socket, so it's going to be lines and lines and lines, where each line is just a string, right? So one of the nice things we can do in the Databricks API is actually call a display on a particular structured streaming data frame that we're interested in looking at, briefly, just to kind of see what's going on, right? So in this case, we can see that we took our logs data frame, and then we use .ag, which is just a function that you'll find on any data frame. And what we're doing is just taking a count here, right? We're just seeing how much, what the current count is. So after I run that, it takes a few seconds, and you can see that the first count we're able to emit based on the data that's coming in was 304. Now that's increased to 2066. So up to this time, we've seen about 3,500 now log messages just coming in. So on the back end, right, so this is where the interface starts to get nice. On the back end, we don't need to keep around every single row of that's coming in, right? We're just computing count aggregation, so we just keep a running sum and increment that. That means we don't actually have an unbounded table. This is why we're not writing out to a table, right? Or excuse me, this is why we don't keep this long table or do something where we just have a regular old Spark streaming, write out everything to a table and then aggregate on that. The Spark engine is a little bit smarter for us here and gives us this nice interface. So we just do a count aggregation and see how much we've gotten in. So you can see this is a reasonably fast stream. In the 30 seconds I was just talking, we had about 10,000 log messages come in. So the next thing we're going to do here is just show off that this is a data frame. And again, this is kind of, from the developer perspective, one of the nicest points of Spark streaming. We're using the exact same API, the exact same interface for the most part, that we would be using in any other kind of data frame application, right? So here, what we're going to do is parse out the timestamp just by using a substring on that. Remember, this is one string that's coming in. We're going to convert that into a timestamp with the sort of hack we've seen a couple of times. And then we pull out any error logs by, first of all, extracting a message string and then looking for anything that contains the word error. So again, these are just data frame operations. And again, if you sort of reason or think about how this actually looks at a streaming level, right, we don't need to keep any data around at all at this point. For every row that comes in, we just check to see does this contain an error. If it does, we're going to write it out to our result table. If it doesn't, then we're not going to do that. So again, while the concept is unbounded input table, the actuality here, the underlying implementation, is smart for us, which is nice. So we start to see those error messages come in, and those are being appended, again, in an unbounded fashion to our result table here. But that's probably, in this case, this sort of writing is probably a feature that we want for our log messages, right? Cool. So the next question we want to figure out is how many records from this log error stream are coming in a given time window. So this is going to allow us to show off what's going on with windowing and how this kind of group by aggregation works in this case over a window. So again, this is all really, really clean and actually gets us to the point that the gentleman over here was asking about or sort of getting at, which is what if we want, kind of operating on the time we receive something versus the time that event happened. So one of the really, really nice things you can do with Spark structured streaming is actually set a column in this input data frame to be your event time. And once we set that event time, let's suppose that for whatever reason, as is kind of the idea here, at around 12:10, a message from 12:07 comes in. We will, Spark structured streaming will take care of all the reasoning involved there to appropriately place that result at the time 12:07 in whatever aggregation windowing we're doing, right? So we start windowing over event time rather than time stuff is actually coming in, which is usually what we care about, I think in most cases.
So did you say that it's bucketed under the event time, or?
Right, so the idea with what we're going to see below is that the event time is going to be a time that's coming in our log message, right? And we're going to use that time to bucket, yes, exactly, rather than the time that we actually receive the message at. And even more than that, we are able to not worry about that sort of implementation detail about when things are coming in, as we might have with RDD-based streaming. And that is just going to correctly be placed in our aggregation or in our result table.
So how does Spark know that how long table should be kept in memory? Because I may get like yesterday's data now, and so all my yesterday's data will be kept in memory.
Sure. So the question is how long does Spark keep this around in memory for? And we'll see there's actually a configurations parameter you can set for how long you want that data to be around in case any more. So we're going to set our window interval, right? But how long you want that data to be around in case more data from in the future actually refers to a past event. So yes, there could be a situation we want to, that's something we want to tune, where we see, okay, what's the kind of top end of how late a message is going to come in, and then once we know that, we can just keep the window open approximately that long. Cool. So again, what we're going to do here is show off some of that windowing. So in particular, we're first going to do the same parsing, so we're actually going to get a timestamp value that we'll be able to window on that we can work with. And here's a new function that we see. So we're just, first of all, we're just using a group by, right? And that's pretty much what we expect. And then the tricky bit here is the windowing that we're doing over this timestamp column. So this is the first place we see that. So we're going to see that our groups are 1 second intervals where every data point that comes in that's event time was at that 1 second interval is added to that group and refreshed every time the data comes in. So let's take a look at how that looks in terms of what Spark Streaming is doing for us. So with 5 minutes left, this query actually takes quite a while. And the issue is we forgot to set our shuffle partition, so we were getting that 200 partitioning issue. There's some checkpointing that happens in Spark Streaming that means that if we shuffle with 200 partitions, those partitions get written out. So that's going to be a very slow thing because of the mapping of state that we're kind of keeping as we journal all of our operations. So in any event, we changed that partition number. So that's again a tuning point you'll probably run into if you start implementing Spark Streaming. And this one should be a bit quicker, and we should see the result of our window here. So you can see what we now do is when we use this windowing function, each of our groups is going to live in the window column, and that's a structured column type. So we actually have a start field inside of each of those and an end field inside of each of those. So we see window.start here, window.end here. And then we're just going to take the count of how many things came in at each point in time. So this should hopefully show us a message in just a second. Yep, there it goes. Here's some of the first information that we're getting in. So we can see that this first window here starts at 54 seconds, ends at 55 seconds, and we can see each of those second intervals happening. So we're going to kill that. Yeah, so the particular parameter we're going to want to set for the problem that you were just asking about is we can set what's called a watermarking time. So as you can see here, this table is going to grow very quickly on our 1 second interval. So one thing we could do would be to just say, okay, let's expand that window, right? Okay, maybe things start growing a bit more slowly. However, if we want to keep track of each of these 1 second windows in our output sync, which is reasonable, right? We might care about what's happening at each of these seconds. Or inside of each of these second intervals, what we can do to make sure that our table doesn't grow to a very large size is set this watermarking configuration option. So again here, just re-highlighting that event time idea. What if stuff comes in late? And the watermarking parameter is going to allow us to set our tolerance for that lateness, right? So here we're saying we only need to keep a minute window of data on that input data frame around, so that we're just bounded to a minute window's worth of data, and we don't worry about it after that. And hopefully, in that case, the data frame we're keeping in memory, if stuff does come out later, we're not going to be able to keep track of that, and that's sort of a trade-off, right?
We ignore that count.
Yeah, exactly. We'll just drop that count. Cool. So I think that's a pretty reasonable place to end here. So the last point I would just briefly mention in this minute or so here is that the next step in building a structured streaming application to make sure that it is sort of production ready is to start thinking about fault tolerance. So with our socket stream that's coming in, right, we consume data from that socket, it's gone. We can't go back and say, hey, TCP socket in the general case, just give me back what you gave me 2 minutes ago or whatever, a minute ago. So one thing we can do to allow for the consistency guarantees that Spark structured streaming can give us is to connect to a replayable data source. So Kafka is a great example of this, where we can actually query for particular offsets in a recent time interval in a particular topic that we care about. And if we do that, again, kind of under the hood, Spark structured streaming is going to take care of missing data. And then on the other side, making sure that we're using sort of journaling output sources allows us to checkpoint and make sure that all of our writes consistently happen in kind of, if you've done databases before, sort of like a databases-y way, right? With nice journaling. So that's all really useful. But it is now 5 o'clock. And yeah, so I'd recommend continuing to go through this lab where it basically goes through a similar analysis, but with the Kafka data source, and from there you can get a feeling for what some of these redundancy guarantees start to look like and what that means, as well as some other interesting visualizations of Wikipedia edits. Sorry? Yeah, I'm sorry about that. Sometimes it happens. We had a lot to cover today, as you know. And yeah, but the good news is this is all here on your Databricks clusters. So what you can do actually is export this information. So I'll just quickly show you how to do that. You just go to Workspace, Export. You can export it as a DBC archive. This will download something to your computer. You can then go and create your own Databricks community account. These ones are going to be closed down in a couple weeks, I want to say. So you can go create your own Databricks community account, upload this DBC archive to your own local community edition cluster, and work from there on this exact same information. Keep going through these notebooks and explore whatever was especially interesting to you. Dive deeper into that and figure out how that might work at your organization. So with that said, thanks everyone so much for coming. I will again highlight that at 6 p.m., where did this slide go? As we walk out, there's a meetup upstairs, the Boston Spark users group that should be a lot of fun, and hope to see you around the conference. Feel free to grab me and chat. Yes? Sorry? Oh, sure. Yes, there is also a Women in Code lunch tomorrow. Is that right?
There's a slide in the student.
Cool. So if you take a look in the student folder, which you can get to, or even on the student reference sheet here, tomorrow, yep, from 12:30 to 2:30 in room 311, there's a lunch for women in big data. So that's again, if that's something you're interested in, should be a really good time. And you can take a look at the information from the reference document.
Are those data still available after 2 weeks?
The data itself, I believe you should be able to mount the, yes. So there's a question which is, if I want to, yep.
Point them to at the top of that SSE 2017 folder.
There's a mount dataset script, right?
Mount
Yep.
notebook, and if you run that will mount the S3 buckets
Yep.
into DBFS. And you can do that in community edition anywhere you want.
Yep. Yeah, exactly as Brian said, just to repeat that. So part one of exporting this data is loading up the DBC file. And then part two is on your local cluster, you'll actually have to mount the data sets. We did that for you today. And you can do that with this datasets mount script that lives right here inside of the SSE 2017 folder. And then, of course, you'll also have to import the libraries and so on and so forth again. So you actually might want to go through the prepare your workspace notebook more generally from there. But yeah, thanks so much, guys.